Imagine for a moment that everything we know about the universe, the swirling galaxies, the invisible forces holding atoms together, even the very nature of reality itself, could have remained hidden forever, if not for a series of beautiful, unpredictable accidents. Some of the most profound truths about our cosmos weren't uncovered through careful calculation or deliberate searching, but revealed themselves in moments of pure serendipity, when a curious mind happened to be looking in just the right place at just the right time. Think about a falling apple leading to the laws of gravity, or a cracked lens accidentally revealing the secrets of light. These aren't just charming stories, they're reminders that some of the greatest leaps in human understanding began with a fortunate mistake, an unexpected observation, or a puzzle that didn't quite fit. Today, we're setting out on a journey through 25 of these astonishing moments, instances where chance and curiosity collided to rewrite the laws of the universe. We'll explore how a mysterious hiss in a radio antenna became the echo of the Big Bang, how a melted chocolate bar opened the door to understanding electromagnetic waves, and how a student's simple observation about freezing water challenged everything scientists thought they knew about thermodynamics. These stories aren't just about science, they're about the human spirit, our relentless drive to question, to explore, and to find meaning in the unexpected. They show us that the universe often speaks in whispers rather than shouts, revealing its secrets not to those who are certain, but to those who are open to wonder. As we delve into these accidental discoveries, you'll witness how they unveiled the existence of dark matter, quantum entanglement, and the fabric of space-time itself. You'll see how a forgotten photographic plate changed our understanding of atomic decay, and how a faint, pulsing signal from deep space turned out to be one of the most precise clocks in the cosmos. Each of these moments didn't just add a new piece to the puzzle, they reshaped the entire picture, showing us that reality is far stranger, more dynamic, and more magnificent than we ever imagined. So join me as we step into a world where luck and curiosity meet, where the universe's greatest secrets are often hiding in plain sight, waiting for someone to notice. The journey begins now. It's a humbling thought that some of the pillars of modern science were built not on flawless blueprints, but on the foundation of fortunate blunders and curious accidents. This isn't a rare exception in the history of progress, it's a central theme. Take the story of penicillin, for instance. Alexander Fleming didn't set out to discover the world's first antibiotic. He returned from a vacation to find a mold called Penicillium notatum contaminating his Petri dishes, and instead of discarding them in frustration, he noticed something miraculous. The bacteria surrounding the mold had been killed. That moment of perceptive curiosity, born from a failed experiment, went on to save countless millions of lives and revolutionized medicine. This pattern of serendipity, the act of finding something valuable while looking for something else, is woven deeply into the fabric of scientific advancement. In the world of astronomy and physics, where we're probing the very edges of reality, this happens with astonishing regularity. A researcher calibrating a new instrument, an engineer troubleshooting an annoying glitch, or a theorist wrestling with a stubborn mathematical inconsistency. These are the moments where the universe often chooses to reveal a new secret. It's as if the cosmos prefers to hide its most profound truths just off the main path, waiting for a traveler with an open mind to stumble upon them. Why is this so common? Perhaps because nature is infinitely more complex and creative than our best models. Our experiments are designed based on what we already know and what we expect to find. But it's the unexpected result, the anomaly that doesn't fit, that often points toward a deeper, previously unimaginable truth. A cracked lens leads to the discovery of new properties of light. A forgotten sample in a drawer reveals the invisible power of radioactivity. A faint, persistent hiss in a massive radio antenna becomes the echo of the universe's birth. These stories teach us that the scientific method isn't just a rigid procedure for testing hypotheses. It's also a framework for recognizing and investigating our own surprises. This tradition of accidental discovery serves as a powerful reminder that the pursuit of knowledge requires not just intelligence, but also humility and a readiness to be wrong. The greatest scientists in history were those who possessed the clarity to see the significance in something they weren't even looking for. As we journey through these 25 groundbreaking accidents, keep this spirit in mind. Each story is a testament to the beautiful collision of human curiosity with cosmic mystery, proving that sometimes the most important thing a discoverer can do is simply pay attention to the unexpected. Now let's dive into our first and perhaps one of the most iconic examples of cosmic serendipity. Picture two brilliant radio astronomers, Arno Penzias and Robert Wilson, working at the legendary Bell Labs in New Jersey in 1965. Their task was seemingly straightforward. They were using a massive, ultra-sensitive horn antenna to study radio waves emitted from our Milky Way galaxy. But their work was being utterly plagued by a persistent, maddening background noise, a constant, uniform hiss that came from every direction in the sky, day and night, and just wouldn't go away. Their first and quite logical assumption was that this was simple terrestrial interference. They meticulously checked every connection, every component of their sophisticated equipment. They even suspected a pair of pigeons had taken up residence in the large horn of the antenna, and famously, they climbed in, cleaned out what they referred to as a white dielectric material, which is the scientific way of saying pigeon droppings, and evicted the birds. Yet, despite their exhaustive efforts, that omnipresent static hiss remained. It was a noise that, by all accounts, had no right to be there. What they had been so desperately trying to eliminate was, in fact, the most important signal in the history of cosmology. That incessant hiss wasn't a flaw in their equipment. It was the faint, cool echo of the universe's fiery birth. They had accidentally stumbled upon the cosmic microwave background radiation. This was the remnant heat from the Big Bang itself, predicted by theorists years earlier but never before detected. Imagine the universe not as a vast emptiness, but as an oven that's been cooling for nearly 14 billion years. That gentle microwave static is the leftover warmth, now just a few degrees above absolute zero, permeating all of space. This discovery was the smoking gun, the conclusive evidence that finally settled a great scientific debate and confirmed that our universe did indeed have a hot, dense, and explosive beginning. The impact of this accidental finding cannot be overstated. It provided overwhelming, direct evidence for the Big Bang theory, catapulting it from a compelling idea to the foundational model of modern cosmology. For this, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. Their work revealed that the entire cosmos is literally bathed in this ancient radiation, a snapshot of the universe when it was just 380,000 years old, a mere infant in cosmic terms. This discovery didn't just tell us how the universe began, it gave us a powerful new tool to understand its composition, its geometry, and its ultimate fate. It opened a window into the primordial conditions that set the stage for the formation of every galaxy, star, and planet that would ever exist. And it all started because two attentive scientists refused to dismiss an annoying bit of static, choosing to investigate the mystery instead of simply ignoring it. Just a few decades before the faint echo of the Big Bang was detected in New Jersey, another world-altering accident was unfolding in a laboratory in Germany. Wilhelm Röntgen, a meticulous physicist, was conducting experiments with cathode rays, streams of electrons in a vacuum tube. His lab was dark, the equipment carefully shielded to contain the rays, but something impossible caught his eye. Across the room, a screen coated with a fluorescent chemical called barium platinocyanide began to glow with a faint, ethereal light. This made no sense. The cathode rays themselves couldn't travel that far, and his apparatus was completely covered in thick black cardboard to block any light. Yet there it was, a ghostly shimmer where none should exist. Röntgen, consumed by a feverish curiosity, dedicated the next several weeks to investigating this baffling phenomenon. He dubbed the mysterious cause Exoplanets, X for unknown, and in a series of ingenious experiments, he discovered their incredible properties. These unknown rays could pass right through solid matter. He found that while they traveled easily through flesh, they were stopped by denser materials like bone or metal. In one of the most iconic moments in scientific history, he placed his wife Anna's hand in the path of the rays with a photographic plate behind it. The developed image revealed the bones of her hand and the shadow of her wedding ring, creating the first ever Röntgenogram. She was reportedly horrified, exclaiming that she had seen her own death. But Röntgen had seen something else entirely, a powerful new window into the invisible world. This serendipitous observation didn't just give doctors a new tool, it fundamentally rewrote our understanding of the universe. Röntgen had accidentally unveiled a vast, previously invisible part of the electromagnetic spectrum. Light wasn't just the narrow band of colors our eyes can see. It included these incredibly energetic rays with the power to penetrate solid objects. This single discovery ignited twin revolutions. In medicine, it transformed diagnosis and treatment almost overnight, allowing physicians to see inside the living human body without a single incision. In physics, it opened the door to the entire field of atomic and high-energy physics. Scientists realized that if such powerful, invisible energy could be produced in a lab, what else was hidden just beyond our perception? The answer came from looking up. We soon discovered that the cosmos is a violent, high-energy arena, and X-rays are its native language. Celestial objects like the superheated gas swirling around black holes, the unimaginably dense cores of neutron stars, and the remnants of colossal supernova explosions all generate torrents of X-rays. But our atmosphere blocks this radiation from reaching the ground, so for decades, this entire cosmic conversation was silent to us. Röntgen's discovery paved the way for the development of X-ray astronomy, leading to space-based telescopes like Chandra and XMM Newton. These observatories have since pierced the veil, showing us a universe teeming with invisible energy, a universe of breathtaking violence and beauty that we didn't even know existed. All because one physicist chose to investigate a faint, mysterious glow in a dark room, rather than dismissing it as a faulty experiment. While Röntgen was unraveling the secrets of X-rays in Germany, a French scientist named Henri Becquerel was pursuing a related question, one that would lead him down an equally unexpected path. Becquerel came from a long line of physicists and was deeply fascinated by the phenomenon of phosphorescence, the ability of certain materials to glow after being exposed to light. He was particularly interested in uranium salts, which exhibited this property. His experiment was straightforward. He would place these salts on a photographic plate, expose them to sunlight to energize them, and then develop the plate, expecting to see an image created by the emitted phosphorescent light. It was a logical, well-designed test, but then the weather in Paris intervened. A spell of overcast skies forced Becquerel to pause his work. He placed his prepared materials, a crystal of uranium salt sitting atop a carefully wrapped photographic plate, into a dark desk drawer to wait for the sun. Days passed, perhaps driven by a combination of frustration and meticulousness. He decided to develop the plate anyway, expecting to see at most a very faint image. What he saw instead was shocking. The plate had been exposed, and not just slightly. A crisp, dark silhouette of the uranium crystal was burned into it. The uranium had been emitting some form of penetrating radiation entirely on its own, without any need for an external energy source like sunlight. This was not phosphorescence. This was something entirely new and fundamentally mysterious. He had accidentally discovered that certain elements are inherently unstable, spontaneously releasing immense energy from within their atoms. He called this phenomenon radioactivity. This single observation shattered the cornerstone of classical physics, the idea of the atom as a solid, immutable, and indestructible billiard ball. Becquerel had inadvertently pulled back the curtain on an entirely new realm of reality, the atomic nucleus. His work revealed that deep within the heart of matter, a hidden, powerful drama was constantly unfolding. Atoms were not placid and eternal. They were dynamic and transient, governed by internal forces of unimaginable strength. This revelation opened a Pandora's box of questions that would consume the next generation of scientists, most notably Marie and Pierre Curie, who took up Becquerel's work, coined the term radioactivity, and discovered new radioactive elements like polonium and radium. The discovery of radioactivity unveiled a world operating on a new set of rules, one where the deterministic, clockwork universe of Newton gave way to the probabilistic and uncertain world of quantum mechanics. Radioactive decay is the ultimate example of this quantum randomness. We cannot predict when a single, specific uranium atom will decay. We can only calculate the probability that it will happen within a certain time frame. For a large sample, this probability manifests as a predictable half-life, but for the individual atom, its fate is governed by chance. This fundamental indeterminacy, first glimpsed in Becquerel's drawer, became a central pillar of the new physics. The implications of this accidental discovery have reverberated through every aspect of modern life, creating a legacy of profound duality. On one hand, it gave us life-saving medical applications. Radioactive isotopes became powerful tools for both diagnosis and treatment, allowing us to track biological processes and target cancer cells with precision. It paved the way for nuclear power, a potent source of low-carbon energy. On the other hand, it unveiled the terrifying potential for nuclear weapons, forever changing global politics and the very nature of warfare. Becquerel's fortunate mistake, born from a cloudy day in Paris, ultimately placed both the promise of limitless energy and the specter of utter annihilation into human hands. It was a stark lesson that our quest to understand the universe's laws does not merely satisfy curiosity. It confers a power that carries immense responsibility, forever reshaping our collective destiny. Meanwhile, across the Atlantic, a different kind of revelation was taking shape, one that would fundamentally alter our cosmic address and our understanding of reality itself. For centuries, the prevailing view of the universe, even among scientists, was largely static and eternal. The cosmos was seen as a vast, unchanging arena where stars and galaxies might move within it, but the stage itself was fixed and permanent. This was the comfortable, intuitive picture, but in the 1920s, an astronomer named Edwin Hubble, working with the powerful new 100-inch Hooker telescope at Mount Wilson Observatory, was about to shatter that illusion forever. His tool was a technique known as spectroscopy, the art of breaking down the light from distant objects into its constituent colors, creating a unique fingerprint called a spectrum. Every element in the universe leaves a specific pattern of dark or bright lines on this spectrum. Hubble and others were using this to measure the velocity of what were then called spiral nebulae, fuzzy patches of light whose nature was hotly debated. Were they simply clouds of gas within our own Milky Way, or were they vast, independent, island universes themselves? As Hubble meticulously analyzed the light from these objects, he noticed something peculiar and consistent. The familiar fingerprint of elements like hydrogen and calcium was there, but the entire pattern was shifted. In nearly every case, the lines were moved toward the red end of the spectrum. This phenomenon, called redshift, is the optical equivalent of the Doppler effect, the same reason a siren's pitch drops as an ambulance speeds away from you. The light waves from these galaxies were being stretched, making them appear redder, which meant they were racing away from us. The real shock wasn't just that most galaxies were fleeing, it was the pattern hidden within their speeds. When Hubble plotted their velocities against their distances, painstakingly measured using a special class of stars called Cepheid variables, he found an astonishingly simple, yet profound, linear relationship. The farther away a galaxy was, the faster it was receding. A galaxy twice as far away was moving twice as fast. This wasn't a random exodus, it was a coordinated, universal flight. This direct correlation became enshrined as Hubble's law, and its implication was nothing short of revolutionary. The entire universe, the very fabric of space itself, was expanding. It wasn't that galaxies were simply moving through a static space. Space itself was stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. This accidental observation, this pattern in the starlight, was the first direct observational evidence for the theory of the Big Bang. It provided a stunning new origin story for the cosmos. If the universe is expanding now, then rewinding the cosmic film means everything was once unimaginably hot, dense, and compact. Hubble's work transformed cosmology from a branch of philosophy into a rigorous observational science. It gave us the Hubble constant, a number that describes the rate of this expansion, which in turn allows us to estimate the age of the universe, placing it at around 13.8 billion years old. Perhaps most poetically, Hubble's discovery gave every galaxy a story written in its light, a story of a shared beginning and a dynamic, evolving future, forever changing our place from the center of a small, static stage to a mere speck in a grand, expanding cosmos. Just a few years after the faint echo of the Big Bang was identified, another mysterious signal began to appear in the data, one so bizarrely perfect that it would briefly convince its discoverer she might have found the first evidence of extraterrestrial intelligence. In 1967, a young PhD student named Jocelyn Burnell was painstakingly analyzing miles of paper chart recordings from a new radio telescope she had helped build in Cambridge. The telescope was designed to study the twinkling of distant quasars, but as Bell sifted through the endless lines of squiggles, something unusual caught her expert eye. It was a tiny, recurring signal, a pulse that appeared in the same patch of sky every 1.337 seconds with a regularity more precise than any atomic clock on Earth. It was unlike any astronomical phenomenon ever recorded. The signal was so unnervingly regular and artificial in its precision that Bell and her supervisor, Anthony Hewish, half-jokingly labeled it LGM-1 for Little Green Men. The notion that it could be a beacon from an advanced civilization was not entirely dismissed in those first thrilling, bewildering weeks. They quietly contemplated the staggering implications while simultaneously working to rule out every possible terrestrial source. from man-made interference to a faulty connection in the vast array of wires and aerials. But the signal persisted, clear and unwavering, and soon they found another one in a completely different part of the sky. This was the crucial clue. It was astronomically impossible for two separate alien civilizations to be signaling Earth at the same time with such similar technology. The truth was far stranger and more spectacular than any science fiction scenario. What Jocelyn Bell had accidentally discovered was the first pulsar, a celestial lighthouse of unimaginable power. A pulsar is the spinning, ultra-dense corpse of a massive star that has died in a supernova explosion. This remnant core, called a neutron star, is a ball of matter so incredibly compact that a single sugar cube-sized piece of it would weigh more than 1 billion tons on Earth. As this neutron star rotates at a ferocious speed, its immensely powerful magnetic field focuses beams of radio waves out from its magnetic poles. If those beams sweep across Earth as the star spins, we detect a pulse of energy with every rotation, just like watching the beam of a lighthouse from a passing ship. The incredible precision of the pulse is simply the rotation period of this cosmic flywheel, a testament to the conservation of angular momentum on a staggering scale. This accidental discovery was a monumental gift to physics and astronomy. Pulsars became nature's ultimate laboratory, allowing us to test the laws of physics under conditions we could never replicate on Earth. Their precise ticks have been used to conduct exquisite tests of Einstein's theory of general relativity. By observing a pair of pulsars orbiting each other, astronomers were able to confirm that they lose energy in the form of gravitational waves, exactly as Einstein predicted, work that would later earn a Nobel Prize. They serve as navigational beacons for potential interstellar travel and provide a natural network for attempting to detect the faint rumble of gravitational waves stretching and squeezing the space between them. Beyond their utility, pulsars unveiled the dramatic and violent end stages of stellar life, showing us that a star's death is not an end but a transformation into something new and extreme. Jocelyn Bell Burnell's sharp eye and intellectual honesty, her refusal to dismiss that tiny, anomalous bit of scruff on her charts opened a window into this hidden world. Her story is a powerful testament to the importance of truly seeing what is in your data, especially when it doesn't fit the expected pattern. The universe, it seems, often saves its most astonishing performances not for those who are only looking for what they expect to find, but for those who are prepared to be surprised. While Jocelyn Bell Burnell was deciphering the precise ticks of cosmic lighthouses, another astronomer was quietly gathering data that would point to a far more pervasive and far more elusive cosmic mystery. Vera Rubin was studying something that seemed, on the surface, far more mundane: how galaxies spin. We all understand the basic principle of a rotating system, from a figure skater pulling in her arms to our own solar system. The planets closer to the Sun, like Mercury and Venus, whip around it at incredible speeds, while the outer worlds like Neptune and Pluto move at a much more sedate, lumbering pace. This is a direct consequence of gravity. The pull of the central mass weakens with distance, so to stay in a stable orbit, an object farther out must move more slowly. For decades, astronomers had simply assumed that entire galaxies, vast islands of billions of stars, would obey this same well-understood rule of orbital mechanics. The stars near a galaxy's bright, crowded center should orbit quickly, while those in the sparse, dark outer regions should crawl along. Armed with a new, highly sensitive spectrometer, Vera Rubin and her colleague Kent Ford began to meticulously measure the orbital velocities of stars in the Andromeda Galaxy, our nearest large galactic neighbor. They expected to see those velocities drop off dramatically as they looked farther from the galactic core, but the data told a completely different story. To their astonishment, the stars at the very edge of the galaxy were hurtling around just as fast as those near the center. It was as if every planet in our solar system, from Mercury to Pluto, orbited the Sun at the exact same breakneck speed. This wasn't just a small anomaly, it was a fundamental violation of Newton's laws of gravity as they were understood. According to the visible mass of stars and gas they could see, the outer stars should have been flung off into the void of intergalactic space by their own centrifugal force. The fact that they weren't meant only one thing: there had to be far, far more mass in the galaxy than they could account for. A huge amount of invisible matter must be providing the extra gravitational glue to hold these rapidly orbiting stars in place. This accidental observation, this stubborn refusal of the data to conform to expectation, was the strongest direct evidence for what we now call dark matter. Rubin's painstaking work on galactic rotation curves forced the entire field of astronomy to confront an uncomfortable truth. The universe we see, the glittering tapestry of stars and galaxies, is just a tiny fraction of the actual universe that exists. The vast majority of matter, roughly 85% of it, is completely invisible. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It neither shines nor casts a shadow. Its presence is betrayed only by its immense gravitational influence, a ghostly hand sculpting the cosmos on the largest scales. We now believe that every galaxy is cocooned within a massive, diffuse halo of this dark matter, a spherical cloud that extends far beyond the galaxy's visible edge, providing the gravitational scaffolding upon which the luminous galaxy is built. The implications of this discovery are staggering and humbling. Dark matter is the great architect of the cosmic web, the invisible framework that guided the formation of galaxies and clusters of galaxies after the Big Bang. Without its gravitational pull, the universe would look utterly different. Galaxies as we know them might never have formed at all. Yet, despite knowing it's there and that it outweighs normal matter by a factor of 5 to 1, we still have no idea what it's actually made of. Is it a sea of exotic, undiscovered subatomic particles, like weakly interacting massive particles that barely interact with normal matter? Or does it require a modification of our fundamental understanding of gravity itself, a tweaking of Newton's and Einstein's laws on cosmic scales? For decades, experiments deep underground and in space have been searching for a direct detection of a dark matter particle, but so far, the mystery remains intact. Vera Rubin's work, driven by a simple question about how galaxies turn, unveiled one of the most profound and enduring puzzles in all of science, a silent reminder that the universe is dominated by forces we can feel but cannot see. While physicists were grappling with the large-scale mysteries of galactic motion, a much smaller but no less profound puzzle was consuming theorists in the world of the very small. The problem was one of confinement and escape. Scientists knew that certain heavy elements like uranium and radium spontaneously emitted alpha particles, a type of radiation consisting of 2 protons and 2 neutrons as they decayed. This process of radioactive decay was well documented, but the mechanism behind it was utterly baffling. Think of an atomic nucleus as a fortress. The alpha particles are trapped inside by what physicists call the strong nuclear force, an immensely powerful barrier that holds the nucleus together. According to the well-established rules of classical physics, for an alpha particle to break free, it would need to be supplied with a tremendous amount of energy to climb over this barrier. It would be like asking a marble to roll up and over the steep lip of a very deep bowl without any extra push. Yet, experiments showed something completely illogical. The alpha particles escaping these nuclei often had far less energy than the classical model said was necessary to overcome the barrier. It was as if the marble was somehow appearing outside the bowl without ever having climbed the side. This wasn't a small discrepancy, it was a fundamental violation of the known laws of physics. The particles simply didn't have the required energy to break out, and yet they were being detected outside the nucleus all the time. For years, this remained a stubborn, unresolved paradox, a clear sign that the comfortable, intuitive rules governing the world we see were completely inadequate for describing the realm of the atom. The solution to this puzzle didn't come from a new experiment, but from a radical new way of thinking. In the late 1920s, a young physicist named Friedrich Hund was working on the mathematical framework of the then nascent theory of quantum mechanics. He was studying how electrons might behave in complex molecules when he accidentally stumbled upon a bizarre mathematical consequence of the theory. Around the same time, other pioneers like George Gamow and independently Ronald Gurney and Edward Kunden were applying this same quantum weirdness directly to the alpha decay problem. What they realized was that in the quantum world, particles do not behave like tiny marbles. They behave like smeared-out waves of probability, and for a probability wave, a barrier is not necessarily an impenetrable wall. This revelation led to the concept of quantum tunneling. Imagine that same energy barrier not as a sheer cliff, but as a tall, thick hill. A classical particle would need enough energy to go up and over the hill. But a quantum particle, with its wave-like nature, has a probability, a chance, of simply appearing on the other side, as if it had dug a tunnel straight through the hill. It doesn't climb the barrier, it effectively cheats. The mathematics showed that this tunneling probability isn't zero. It's a small number, but it's real. The lower the energy of the particle and the thicker the barrier, the lower the probability, but it never quite drops to absolute zero. This meant that even a particle with seemingly insufficient energy has a tiny, but non-zero, chance of spontaneously appearing on the other side of an energy barrier that should be impossible to cross. This wasn't a theory of magic, it was a direct, mathematically sound prediction of quantum mechanics. It was the key that finally unlocked the mystery of alpha decay. The particles weren't defying physics, they were operating under a deeper, more bizarre set of quantum rules. The implications of this accidental theoretical insight are almost endless, reaching far beyond explaining a single type of radioactive decay. Quantum tunneling is not a rare, exotic phenomenon. It is a fundamental process that underpins the very existence of our sun and stars. At the core of our sun, the temperature and pressure are immense, but by classical standards, they are still not quite high enough to force positively charged protons to overcome their mutual electromagnetic repulsion and fuse together. It is only through the magic of quantum tunneling that protons can occasionally tunnel through that repulsive barrier, allowing nuclear fusion to occur and providing the energy that lights and heats our world. Without tunneling, the sun would be dark and the universe would be a very different place. This quantum cheat code is also the bedrock of modern electronics. The semiconductor chips in your computer, phone, and countless other devices rely on transistors, and the operation of those transistors depends on electrons tunneling through barriers. It allows for the incredible miniaturization and speed that defines our technological age. The scanning tunneling microscope, a revolutionary invention that earned its creators the Nobel Prize, literally uses the tunneling current of electrons to map the surfaces of materials atom by atom, letting us see and manipulate the nanoscale world. Even life itself harnesses this quantum quirk. In the process of photosynthesis, plants use the energy from sunlight to create chemical energy. Research suggests that the incredibly high efficiency of this energy transfer might be due to quantum tunneling, allowing energy to find the most efficient path through the plant's cellular machinery almost instantaneously. What began as a theoretical solution to a frustrating problem in nuclear physics unveiled a universe that operates on a foundation of probability and potentiality. Quantum tunneling forces us to abandon the clockwork, deterministic universe of Newton and accept a reality where outcomes are not certain but probable. A particle can be in a place it has no right to be, simply because the laws of the universe allow for that vanishingly small possibility. This discovery exemplifies the incredible power of pure theoretical curiosity. Hund, Gamow, and the others weren't in a lab. They were working with chalkboards and equations, following the math wherever it led, even when it led to conclusions that defied all common sense. Their work proved that the deepest truths about reality are often hidden not in what we can directly observe, but in the elegant, if bewildering, language of mathematics. While physicists were wrestling with the bizarre quantum rules governing the subatomic world, a different kind of discovery was unfolding in the seemingly more mundane field of atmospheric chemistry, one that would prove humanity itself had become a powerful and potentially destructive geological force. The story begins not with a lone scientist in a lab, but with a ubiquitous consumer product, the aerosol spray can. In the 1970s, compounds known as chlorofluorocarbons, or CFCs, were the wonder chemicals of the modern world. They were non-toxic, non-flammable, and incredibly stable, making them the perfect propellants for everything from hairspray and deodorant to refrigerants and air conditioning units. They were considered so safe and inert that the very idea they could pose an environmental threat seemed almost laughable. They were the last thing anyone would have suspected of causing planetary harm. It was this very perception of safety that drew the attention of two chemists at the University of California, Irvine, Mario Molina and F. Sherwood Rowland. They weren't environmental activists, they were curious scientists fascinated by the ultimate fate of these incredibly stable molecules. They knew that CFCs, once released from a spray can or a leaky refrigerator, didn't just disappear. Their stability meant they didn't break down in the lower atmosphere. Instead, they slowly, inexorably drifted upward, carried by air currents on a years-long journey into the stratosphere, the layer of the atmosphere that begins about 6 miles above the Earth's surface. Molina and Rowland began to model what might happen to these molecules when they reached such dizzying heights, where they would be bombarded by the sun's powerful ultraviolet radiation. What they discovered was a chemical time bomb, that intense UV radiation which the CFC molecules were never exposed to down on the ground, had enough energy to break them apart. This process, called photodissociation, shattered the stable CFC molecules, releasing individual chlorine atoms, and this is where their work took a terrifying turn. They realized that a single chlorine atom, once set free in the ozone layer, could act as a ruthless and efficient catalyst. It could attack an ozone molecule, a fragile structure of 3 oxygen atoms, and break it apart into regular oxygen. The sinister part was that the chlorine atom itself emerged from this reaction unscathed and ready to do it all over again. One single chlorine atom could destroy not one, but tens of thousands of ozone molecules before it was finally removed from the atmosphere. Molina and Rowland had accidentally uncovered a chain reaction of staggering destructive potential, a process that was silently eating away at the planet's primary shield against harmful solar radiation. Their 1974 paper was a wake-up call that landed like a thunderclap. They had revealed that humanity, through the widespread use of these harmless chemicals, was inadvertently punching holes in our own planetary sunscreen. The ozone layer is not just a scientific curiosity, it is a vital piece of planetary infrastructure. It absorbs more than 97% of the sun's high-frequency ultraviolet light, radiation that is powerful enough to damage DNA, cause skin cancers and cataracts, and disrupt the delicate balance of entire ecosystems, particularly phytoplankton at the base of the oceanic food web. Without it, complex life on Earth's surface would be severely threatened. The idea that our convenience was directly threatening this shield was both shocking and horrifying. The initial reaction from the chemical industry was fierce denial and aggressive pushback, a playbook that would become unfortunately familiar in later environmental debates. Melina and Roland were criticized, their models questioned, but they persisted, and the evidence soon became undeniable. In 1985, a team of British scientists working in Antarctica reported a discovery that shocked the world: a massive, recurring hole in the ozone layer right above the South Pole. The satellite images were unmistakable and chilling. The theoretical prediction had become an observational reality, and it was far worse than anyone had anticipated. The world was suddenly faced with a clear, present, and man-made danger of a truly global scale. But this is where the story transforms from a cautionary tale into a monumental success story for international cooperation. The scientific evidence was so overwhelming, and the potential consequences so dire, that the world's governments were compelled to act with unprecedented speed and unity. In 1987, just over a decade after Melina and Roland's initial paper, nations signed the Montreal Protocol on substances that deplete the ozone layer. It was a landmark global agreement to phase out the production of CFCs and other ozone-depleting chemicals. What makes the Montreal Protocol so remarkable is that it was the first United Nations treaty in history to achieve universal ratification. Every single country on Earth is a party to it. It has been strengthened over the years and is widely regarded as the most successful international environmental agreement ever enacted. The results speak for themselves. The production of ozone-depleting substances has plummeted by more than 99%. Scientists project that the ozone layer is now on a slow but steady path to recovery, with the Antarctic ozone hole expected to heal completely by around the middle of this century. The Montreal Protocol did more than just save the ozone layer. It also had an enormous, unintended benefit for the climate. Many of the chemicals it banned are also potent greenhouse gases, so the treaty accidentally became one of the single most effective actions ever taken to mitigate climate change. The work of Melina and Roland, which began with a simple question about the journey of a molecule, unveiled a profound truth: that human ingenuity can both create global problems and, through vigilance, cooperation, and scientific courage, solve them. It stands as a powerful testament to the idea that when science sounds the alarm, the world can indeed listen, learn, and act for the greater good of the entire planet. While the world was grappling with the invisible threat to our atmosphere, a completely different kind of invisible phenomenon was being uncovered in a Dutch laboratory, one that promised a future of incredible technological potential. The quest to understand matter at its coldest possible temperatures was the obsession of a physicist named Henri Kamerlingh Ons. At his cryogenics lab in Leiden, he had achieved what was then a monumental feat: liquefying helium, bringing it to a bone-chilling 4.2 degrees above absolute zero. Absolute zero, the theoretical point where all atomic motion ceases, is the ultimate limit of cold, and Ons was pioneering the tools to get closer to it than anyone ever had before. His goal was to study how the electrical properties of metals changed when they were subjected to such an unimaginable deep freeze. He selected mercury for one of his experiments, a pure metal that he could easily distill and purify into a fine wire. As he slowly bathed the mercury wire in the frigid liquid helium bath, he meticulously measured its electrical resistance. The classical understanding of physics predicted a clear outcome. Resistance, the property that makes a material oppose the flow of electric current and turn some of that energy into waste heat, was expected to decrease steadily as the metal got colder. The jostling atoms that cause resistance would slow down, allowing electrons to flow more freely. But the expectation was that this resistance would never truly hit zero. It would simply approach it asymptotically, getting closer and closer without ever quite reaching that perfect state. What Arns and his team witnessed defied all expectations. As the temperature dropped past a critical threshold, around 4.2 Kelvin, the electrical resistance of the mercury didn't just get very, very low. It plummeted abruptly and completely to absolutely nothing. It vanished entirely. The current he had introduced into the wire wasn't just flowing, it was flowing perpetually with zero energy loss. He had stumbled into a startling new phase of matter, which he named superconductivity. This was a discovery so bizarre it seemed to violate the fundamental laws of thermodynamics. In any normal circuit, you need a constant power source, like a battery, to push current through because resistance constantly saps that energy. But here, in this supercooled state, the current was self-sustaining. Arns famously demonstrated this by inducing a current in a loop of superconducting lead and then removing the battery. The current continued to circulate for days on end without any measurable decrease. He had accidentally created the closest thing to perpetual motion the universe allows, a direct consequence of this complete loss of resistance. The implications were immediately staggering. Imagine transmitting electricity across continents without losing a single watt to heat. Imagine building electromagnets of unimaginable power that required virtually no energy to maintain their immense magnetic fields. Arns had unlocked a phenomenon that seemed almost magical, and it would take nearly half a century of brilliant theoretical work to unravel its quantum secrets. The true explanation for why superconductivity occurs is a masterpiece of quantum mechanics, a world where the rules of our everyday experience completely break down. In a normal metal, electrons are individualists. They bump and jostle against the vibrating atoms of the material, and this chaotic movement is what we measure as electrical resistance. They are like a crowd of people all trying to push through a narrow hallway at once, constantly colliding with each other and the walls, losing energy and momentum with every step. But in the strange, ordered world of a superconductor, something miraculous happens. At these ultra-low temperatures, electrons, which normally repel each other because of their negative charges, are forced into an unlikely partnership. Through an interaction with the vibrating lattice of the metal itself, they form what are called Cooper pairs. Think of it like this. As one negatively charged electron moves through the lattice, it slightly attracts the positively charged ions around it, creating a tiny, momentary region of greater positive charge. This slight distortion can then attract a second electron, effectively binding the two together into a paired state. This pairing is incredibly fragile and only survives in the extreme cold where atomic vibrations are minimal. These Cooper pairs don't behave like individual electrons anymore. They condense into a single, coherent quantum state, a giant collective where all the pairs move in lockstep. It's no longer a disorderly crowd. It's a perfectly synchronized marching band moving through the material. Because they are all acting as one, they can no longer scatter off individual atoms. They flow around any imperfections or obstacles without any friction or loss of energy. This collective behavior, described by the groundbreaking BCS theory, named for John Bardeen, Leon Cooper, and John Robert Schrieffer, is what allows for the magic of zero resistance and the perfect, lossless conduction of electricity. This accidental discovery in a Leiden lab has since rippled out to touch nearly every facet of modern technology. the most visible application is in medical imaging. The powerful magnets at the heart of every MRI machine are superconducting electromagnets. Without superconductivity, creating a magnetic field that's strong and that stable would be impossibly expensive and energy-intensive, as the electrical currents required would generate catastrophic amounts of waste heat. Superconducting magnets are also the indispensable workhorses of particle physics, bending and focusing beams of particles at near light speed inside massive rings like the Large Hadron Collider at CERN. But the applications are pushing far beyond these established uses. The emerging field of quantum computing relies heavily on superconducting circuits to create and manipulate quantum bits or qubits. In these devices, the coherent motion of Cooper pairs is used to create and maintain the fragile quantum states necessary for computation. We are also on the cusp of realizing superconducting power grids, maglev trains that levitate frictionlessly over tracks, and even novel electronic devices that operate with unparalleled efficiency. Kamerlingh-Onnes's fortunate experiment didn't just reveal a new material property. It opened a portal to a world governed by collective quantum behavior, a world we are still learning to harness, promising a future built on the effortless, frictionless flow of energy. Albert Einstein's theory of general relativity completely reimagined gravity, not as a simple force of attraction, but as a curvature in the very fabric of spacetime itself. He proposed that massive objects, stars, galaxies, black holes warp the space around them, much like a heavy bowling ball would stretch and distort a taut rubber sheet. Any object moving through this warped space, he theorized, would have its path bent by the curvature. This included even light itself, which has no mass. In 1919, this stunning prediction was first confirmed during a solar eclipse, when the sun's gravity was observed to subtly deflect the light from distant stars, making them appear slightly out of place. It was a monumental victory for his theory, but this was just a tiny taste of the cosmic distortions that were possible. For decades, this bending of light remained a small, delicate effect, something only measurable during the rare and precise conditions of an eclipse. But Einstein's equations hinted at something far more dramatic. If the mass was large enough and aligned perfectly, the warping of spacetime could be so extreme that it wouldn't just bend light. It could act like a lens, focusing, distorting, and even multiplying the image of an object lying far behind it. Einstein himself thought this perfect alignment, which could create multiple images or even a complete ring of light, would be too rare to ever actually be observed. It seemed like a theoretical curiosity, a beautiful but unreachable consequence of the math. Then, in 1979, a team of astronomers made a completely unexpected find. They were studying an object known as a quasar, an incredibly bright beacon of light powered by a supermassive black hole at the heart of a distant galaxy. This particular quasar, catalogued as 0957 plus 561, looked utterly bizarre. Instead of a single point of light, their images showed two identical, closely paired quasars. The immediate, thrillingly bizarre possibility was that they had discovered a binary quasar system, two of these cosmic powerhouses orbiting one another. But the spectra of the two objects told a different story. They were exactly identical, the same redshift, the same emission lines, the same everything. It was statistically impossible for two separate quasars to be so perfectly matched. The only logical conclusion was that they were not two objects at all, but two separate images of the very same single quasar, billions of light years away. The culprit was a faint, foreground galaxy sitting directly in the line of sight between Earth and the distant quasar. This galaxy's immense gravitational field was warping the spacetime around it so profoundly that it was bending the quasar's light rays, pulling them along different paths around its edges. Some of these light rays took a slightly longer route to the left of the galaxy, while others took a different path to the right. From our vantage point on Earth, it appeared as if the light was coming from two distinct locations in the sky. They had accidentally discovered the first clear example of a gravitational lens, a phenomenon that was immediately and poetically dubbed Einstein's cross when later examples revealed not just two, but four distinct images arranged in a symmetrical pattern around the lensing galaxy. This serendipitous discovery transformed a beautiful theoretical idea into an observational workhorse for modern cosmology. Gravitational lensing is much more than a cosmic illusion. It is one of astronomy's most powerful tools. First, it provided the most direct and robust test of general relativity on a truly galactic scale, confirming that Einstein's equations hold true even over these immense distances and with these tremendous masses. But its utility goes far beyond simply validating old theories. The way the light is bent depends directly on the mass of the foreground lensing object. This means astronomers can use gravitational lensing to literally weigh galaxies and clusters of galaxies. And when they do this, they consistently find that the amount of mass required to create the observed lensing effect is far greater than the mass we can see in the form of stars and gas. This is some of the strongest independent evidence for the existence of dark matter, allowing us to map out its distribution in the halos around galaxies in exquisite detail. Perhaps even more impressive is its use as a natural telescope. The lensing effect can magnify the light of incredibly distant, faint galaxies that would otherwise be far beyond the reach of our largest man-made observatories. By looking through these cosmic magnifying glasses, we can peer back to some of the earliest galaxies ever formed, studying the infancy of the universe with a clarity we could never achieve on our own. This accidental discovery of a double image in the sky unveiled a universe that is not only stranger than we imagine, but one that actively helps us see it more clearly, using the very warp and weft of spacetime as a lens to reveal its own deepest secrets. For decades, physicists had assembled an increasingly successful and yet deeply puzzling map of the subatomic world, known as the Standard Model. This framework brilliantly described the particles that make up matter like electrons and quarks, and the forces that govern their interactions, such as electromagnetism. But there was a gaping hole in this otherwise elegant theory, one so fundamental it threatened to unravel the entire structure. The problem was mass. According to the pure, symmetric mathematics underlying the model, all of these fundamental particles should be massless, zipping around the universe at the speed of light. But we know that's not true. Electrons have mass, the quarks that form protons and neutrons have mass. If the theory was correct, then atoms could never form, and neither could stars, planets, or people. Something had to be breaking this perfect symmetry, something that was granting mass to particles and making our material universe possible. But what? This was the theoretical puzzle that a handful of physicists, including Peter Higgs in the UK and Francois Inglet and Robert Brout in Belgium, were wrestling with in the 1960s. They weren't trying to discover a new particle. They were trying to solve a deep problem in quantum field theory. Independently, they stumbled upon a breathtakingly elegant and radical solution. What if empty space isn't really empty at all? What if the entire universe is permeated by an invisible, omnipresent field, now known as the Higgs field? Imagine this field not as a thing made of particles, but more like a vast, intangible ocean or a cosmic vat of invisible molasses that fills every cubic inch of the vacuum of space. Their brilliant, accidental insight was that this field interacts with fundamental particles in a way that endows them with mass. The mechanism is often explained by an analogy of a famous person moving through a crowded room. A massless particle, like a photon of light, would zip through this Higgs field completely unaffected, like an unknown person who attracts no attention and can move through the crowd at full speed. They remain massless, but other particles, like electrons or quarks, interact with this field. It's as if they are the famous celebrities. The field clings to them as the crowd would swarm around the celebrity, making it much harder for them to move. This resistance to acceleration is exactly what we experience and measure as inertia or mass. The stronger a particle interacts with the Higgs field, the more mass it has. This mechanism didn't just plug a hole in the theory, it explained the very origin of mass itself, providing a mathematical reason why some particles are heavy and others are light. But a field like this, according to quantum theory, must have an associated particle, a ripple or excitation in the field. This was the predicted Higgs boson. Finding this particle would be the ultimate proof that the Higgs field was real. The challenge was monstrous. The theories suggested the Higgs boson would be immensely heavy and unstable, decaying into other particles in a fraction of a nanosecond. To create it, we would need to concentrate a staggering amount of energy into a tiny space, recreating the conditions of the universe a trillionth of a second after the Big Bang. No machine on Earth was remotely powerful enough. The hunt for the Higgs boson became the holy grail of particle physics, a quest that would require decades of technological innovation, billions of dollars, and the collaboration of thousands of scientists from around the globe. The instrument built to find it is perhaps the most complex machine ever constructed, the Large Hadron Collider at CERN. Buried 300 feet beneath the Franco-Swiss border, this 17-mile ring is a cathedral of pure science. Inside, protons are accelerated to 99.9999991% of the speed of light and smashed together head-on in colossal detectors the size of cathedrals. These collisions briefly unleash temperatures 100,000 times hotter than the core of the Sun, creating a fireball of primordial energy from which new particles, like the Higgs, can momentarily blink into existence. For years, the teams operating the two main detectors, ATLAS and CMS, sifted through the debris of trillions upon trillions of these collisions, searching for the faint, telltale signature of a Higgs boson's instantaneous decay. Then, on the 4th of July 2012, the world watched as the leaders of the two experiments announced their results to a packed auditorium. The tension was palpable. The data slides went up, showing a clear, unambiguous bump in their data at an energy of around 125 gigaelectronvolts. It was the signal. The Higgs boson had been found. The room and the global physics community watching online erupted in a moment of pure, unadulterated joy and profound relief. This wasn't just the discovery of another particle. It was the validation of a 50-year-old theoretical dream, the final, missing piece of the Standard Model. It confirmed that our universe is indeed filled with this cosmic treacle, the Higgs field, which gives everything its substance. It explained why we, and everything we see, have the mass to exist at all. The discovery was a monumental testament to human curiosity, a celebration of how a beautiful abstract idea, born on a chalkboard, can be proven to be a tangible truth about our reality through sheer ingenuity and perseverance. While the discovery of the Higgs boson filled a crucial gap in our understanding of particle mass, cosmologists were wrestling with cosmic-scale puzzles that the standard Big Bang model simply couldn't solve. The universe, when examined on its largest scales, presented astronomers with two deeply confusing mysteries known as the horizon problem and the flatness problem. The horizon problem asks why the universe looks so incredibly uniform in every direction we look. the cosmic microwave background radiation, that faint echo of the Big Bang discovered by Penzias and Wilson, shows almost exactly the same temperature everywhere to within 1 part in 100,000. This might not sound strange until you consider that light, and therefore information or influence, has a finite speed. There hasn't been enough time since the Big Bang for heat to have flowed from one distant region of the universe to another to even out these temperatures. It's like walking into a massive concert hall and finding that every single seat, even those on opposite sides, are all exactly 68.4 degrees, without any apparent way for the temperature to have equalized. The universe, according to the classic Big Bang timeline, shouldn't have had time to mix itself into this perfect smoothness. Then there's the flatness problem, which is perhaps even more bizarre. The density of matter and energy in the universe appears to be exquisitely fine-tuned to a very specific, critical value. Imagine the fate of the universe as a ball being thrown into the air. If the ball has too much kinetic energy, it will escape Earth's gravity entirely and fly off into space forever. This would be an open universe destined for eternal expansion. If the ball has too little energy, it will eventually fall back to the ground, a closed universe that will one day collapse in a big crunch. But if the energy is just perfectly balanced, the ball will reach a point where it is almost, but not quite, at escape velocity, hovering at the threshold. This is the flat universe. The problem is that for our universe to appear as flat as it does today, 14 billion years after the Big Bang, its initial density at the moment of birth had to be fine-tuned to an unimaginable precision of 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. It would be like balancing a pencil on its tip and coming back a billion years later to find it still perfectly upright. The odds of this happening by chance are so astronomically low that it strongly suggested some fundamental physical process must have forced the universe into this flat state. The man who accidentally stumbled upon the solution to both of these problems in one elegant sweep was a young particle physicist named Alan Guth. In the late 1970s, Guth wasn't even working on cosmology. He was deep in the world of grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework. He was studying the behavior of certain hypothetical fields that might have existed in the incredibly hot, early universe. These fields can undergo what are called phase transitions, much like water freezing into ice. But Guth realized that under the extreme conditions just after the Big Bang, one of these phase transitions could get stuck. The field would become trapped in a bizarre, high-energy state known as a false vacuum. And this false vacuum had a truly astonishing property. It could generate a repulsive gravitational force. This was the moment of serendipity. Guth, a particle physicist, suddenly saw the cosmological implications. He famously scrawled in his notebook, "Spectacular realization." If this false vacuum state with its repulsive gravity had briefly dominated the universe, it would have caused a staggering, exponential expansion. He calculated that in an almost incomprehensibly tiny fraction of a second, from 10 to the power of -36 seconds to perhaps 10 to the power of -32 seconds after the Big Bang, the universe could have doubled in size not once or twice, but perhaps 100 times over. This period of hyper-expansion, which he dubbed inflation, would have blown up a subatomic-sized region of space into something larger than our entire observable universe today. This single, brilliant insight solved both cosmic puzzles in one fell swoop. The horizon problem vanished because the entire observable universe was, in fact, inflated from a tiny, pre-inflationary patch that had plenty of time to become smooth and uniform before being stretched across the cosmos. The flatness problem was solved because inflation would have acted like a cosmic carpenter, taking any initial curvature in space-time and stretching it so dramatically that it would appear perfectly flat to any observer inside it, just as the surface of a blown-up balloon appears flatter and flatter the bigger it gets. Inflation didn't just solve old problems, it made dramatic new predictions. It said that the seeds for all the structure in the universe, the galaxies, clusters, and vast cosmic web should have originated from microscopic quantum fluctuations in that primordial inflaton field. These tiny, random ripples would have been stretched to astronomical sizes by inflation, creating slight variations in density that, over billions of years, would gravitationally collapse into everything we see today. Most importantly, it predicted a very specific pattern of faint temperature variations in the cosmic microwave background, a signature that would later be confirmed with stunning precision by satellites like COBE, WMAP, and Planck. This confirmation turned inflation from a compelling idea into the cornerstone of modern cosmology. Guth's spectacular realization, born at the intersection of particle physics and gravity, gave us a new, breathtaking narrative for the very first moments of creation, a story of a universe bursting into being from almost nothing, setting the stage for all that was to come. Deep beneath the Black Hills of South Dakota, in the hushed darkness of a former gold mine, one of the most audacious and perplexing experiments in the history of science was taking shape. Raymond Davis Jr., a chemist with a physicist's ambition, was building a machine unlike any other. His goal was to catch ghosts. More specifically, he was trying to detect neutrinos, the most elusive, ethereal particles in the universe streaming from the heart of our sun. The theory was beautiful and seemingly straightforward. The sun's powerful nuclear furnace, fusing hydrogen into helium, should produce a torrent of these particles. Billions of them were passing through every square centimeter of the Earth and through our bodies every second. They interact with matter so rarely that to them, our planet is almost completely transparent. Davis's challenge was to catch just a handful of these phantoms, to prove that we truly understood the engine that powers our star. His solution was a masterpiece of minimalist ingenuity. He built a colossal tank containing 615 tons of perchloroethylene, a common industrial cleaning fluid. His logic was exquisitely precise. Very, very occasionally, a neutrino from the sun should interact with a chlorine-37 atom in this vast vat of fluid. When it did, it would transmute that chlorine atom into a radioactive isotope of argon-37. His entire experiment was designed to be a cosmic fishing net. Every few months, he would flush his giant tank with helium gas to bubble out and collect the few dozen atoms of argon that might have been created. He would then place these captured atoms in a radiation counter to see them decay, each decay a tiny signature proving that a neutrino had been there. It was like finding a few specific grains of sand on all the beaches of the world. The painstaking process was slow, difficult, and required unimaginable patience. But after years of running this delicate operation, Davis had a result, and it was deeply, profoundly wrong. According to the best solar models developed by the pioneering astrophysicist John Becquerel, Davis's tank should have been catching about 1 solar neutrino interaction per day. But he was only catching about 1 every 3 days. He was only detecting a third of the neutrinos that the brilliant, shining sun above us insisted must be there. For years, this discrepancy was dismissed. Surely the error was with Davis's impossibly difficult experiment, not with our understanding of the sun itself. Perhaps his chemistry was flawed. Perhaps there was some background contamination he hadn't accounted for. The idea that the foundational models of stellar physics were incorrect seemed far more unlikely than a single experiment being off. This was the birth of the solar neutrino problem, a mystery that would gnaw at the very foundations of physics for over 30 years. Davis, however, was certain of his meticulous work. He trusted his data, and his stubborn persistence in the face of widespread skepticism transformed a potential experimental error into one of the most important puzzles in modern science. The solution to this problem did not come from building a better chlorine tank. It came from building entirely different kinds of detectors, ones that could not only detect neutrinos but also tell what type of neutrino they were. This is where the story takes a bizarre and wonderful turn into the quantum weirdness of particle identity. Theorists had begun to propose a radical idea. What if the neutrinos produced in the Sun were not disappearing? What if they were simply changing their identity on the long journey to Earth? The standard model of particle physics, that incredibly successful rulebook for the subatomic world, stated that neutrinos were massless. And if they were massless, they should travel at the speed of light and be frozen in their identity forever. An electron neutrino would always be an electron neutrino. But if, against all expectations, neutrinos had even a tiny, minuscule amount of mass, then a strange quantum phenomenon called oscillation could occur. A neutrino could literally morph between its three different flavors, electron, muon, and tau, as it traveled through space. The Sun only produces electron neutrinos. Davis's experiment was only sensitive to electron neutrinos. The tantalizing possibility was that by the time they traveled 93 million miles to Earth, 2/3 of them had oscillated into muon or tau neutrinos, rendering them invisible to his detector. Confirming this wild idea required a new generation of experiments that could see the full neutrino spectrum. In the late 1990s and early 2000s, detectors like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada finally provided the definitive answer. They could detect neutrinos by watching for the faint flash of light created when a neutrino bumped into an electron in a vast tank of ultra-pure water. More importantly, they could tell what direction the neutrino came from and were sensitive to all three flavors. The data was incontrovertible. The total number of neutrinos arriving from the Sun matched the solar models perfectly. But only 1/3 of them were still electron neutrinos. The other 2/3 had indeed changed into the other types during their journey. Raymond Davis Jr., who had been doggedly counting atoms in a South Dakota mine for decades, was finally vindicated. The problem wasn't with the Sun, and it wasn't with his experiment. The problem was with the laws of physics as we knew them. This accidental discovery, born from a stubborn discrepancy, sent shockwaves through the world of physics. Neutrino oscillation proved unequivocally that neutrinos must have mass. It was a small mass, mind you, so small that we still haven't been able to measure it directly with the required precision, but it was definitively not zero. This was a monumental discovery. The standard model, which had predicted massless neutrinos, was now proven to be incomplete. It was the first clear, irrefutable evidence of physics beyond the standard model, discovered not in a multi-billion-dollar collider, but by watching the Sun and trusting an anomaly. This revelation forced a fundamental rewrite of our understanding of the universe's most abundant particles with mass. It opened up entirely new questions about the role these ghostly particles played in the cosmos. Their tiny mass, multiplied by their unimaginable abundance, means they likely play a crucial role in the gravitational pull that shapes the universe's largest structures. They are key players in the violent deaths of massive stars as supernova, where they carry away 99% of the star's energy in a spectacular burst. The story of the solar neutrino problem is a powerful testament to the importance of paying attention when nature gives us a number that doesn't fit our expectations. It shows that the universe's deepest secrets are often hidden not in the grand confirmations of our theories, but in the quiet, persistent whispers of their failures. For centuries, the fundamental narrative of the cosmos seemed settled. Ever since Edwin Hubble revealed the universe was expanding, the central question for cosmologists was not if this expansion would continue, but how fast it would slow down. The entire story was governed by gravity, the great cosmic glue. After the initial impulse of the Big Bang, the mutual gravitational attraction of every galaxy, star, and speck of dust in the universe was expected to act as a brake, relentlessly pulling on the expansion, gradually slowing it down over billions of years. The ultimate fate of the cosmos hinged on this deceleration. Would there be enough matter to eventually halt the expansion and pull everything back together in a fiery, big crunch? Or would the universe just keep expanding forever, growing ever colder and more diffuse? This was the grand debate. No one in their wildest dreams imagined the expansion might be speeding up. In the late 1990s, two independent teams of astronomers set out to settle this very question by measuring the rate of this cosmic deceleration with exquisite precision. Their tool was a special class of stellar explosions known as Type 1a supernova. These are not just any supernova, they are nature's perfect standard candles. They occur in binary star systems where a dense white dwarf star steals material from its companion. Once the white dwarf reaches a very specific, critical mass, a threshold known as the Chandrasekhar limit, it undergoes a runaway nuclear explosion. Because this trigger mass is always the same, the intrinsic brightness of these explosions is always nearly identical. This makes them phenomenal cosmic mile markers. By carefully measuring how bright these supernovae appear to us here on Earth, astronomers can calculate their precise distance, and by measuring the redshift of their host galaxies, they can determine how fast the universe was expanding at the time the star exploded. By looking at supernova in extremely distant galaxies, they were effectively looking back in time, mapping out the expansion history of the universe. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were engaged in a friendly but intense scientific race. They were pushing the limits of technology, using the world's most powerful telescopes and sophisticated digital cameras to hunt for these rare, fleeting cosmic beacons in the deep, dark sea of space. They painstakingly collected their data, expecting their results to plot a graceful curve showing the universe's expansion gradually slowing down. But as they analyzed their findings, a sense of profound disbelief began to set in. The distant supernova, the ones that exploded billions of years ago, were significantly fainter than they should have been. According to their models, which factored in all known physics, these supernovae needed to be farther away than their redshift measurements indicated. The only possible explanation was that the universe wasn't expanding at a constant or decelerating rate. The expansion was accelerating. The most distant galaxies were flying away from us faster today than they were in the past. It was as if you threw a ball into the air, and instead of slowing down as gravity pulled on it, it shot away from you faster and faster into the sky. The result was so shocking that both teams spent months frantically searching for a mistake, a systematic error in their data. They checked and rechecked their work, considering everything from intergalactic dust dimming the starlight to potential evolution in the supernova themselves. But the data was robust, the conclusion was inescapable. The universe's expansion was not slowing down, it was speeding up. This accidental discovery was arguably the most baffling and revolutionary in cosmology since Hubble's own work. Gravity, the force that shapes the cosmos on every scale, from apples falling to planets orbiting, was being overpowered by something else on the grandest scale of all. There had to be a mysterious, repulsive force counteracting gravity's relentless pull, a force woven into the very fabric of space itself. This unknown entity was christened dark energy. The name reflects our profound ignorance. We know it's there because of what it does, but we have no idea what it actually is. The most mind-boggling implication of this discovery is the sheer dominance of dark energy. When cosmologists calculated how much of the universe's total mass energy budget this force must account for to produce the observed acceleration, the number was staggering. Dark energy makes up approximately 68% of the universe. Combined with the 27% comprised of dark matter, this means that 95% of the entire cosmos is made of stuff we cannot see and do not understand. The ordinary atoms that make up stars, planets, and us, everything we've ever known and studied, constitute a mere 5% of the whole. This revelation sent theorists scrambling back to their chalkboards. The leading candidate for an explanation is something Albert Einstein proposed and later famously rejected as his biggest blunder: the cosmological constant. This is the idea that empty space itself possesses a fundamental energy density, a constant pressure that causes space-time to expand. The more the universe expands, the more of this vacuum energy there is, leading to a runaway acceleration. Other theories propose a dynamic field nicknamed quintessence that changes over time, unlike the static cosmological constant. But despite decades of intense study, dark energy remains the deepest mystery in physics. Its discovery, which earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, is a humbling reminder of how little we truly know. It overturned a fundamental assumption about the cosmos and revealed that the universe is not only stranger than we imagine, but stranger than we can imagine, dominated by a mysterious force that is silently, inexorably, steering its ultimate fate toward a cold, dark, and lonely end. Even as the unsettling reality of dark energy was reshaping our understanding of the cosmos on the grandest scale, a different kind of revolution was brewing in the realm of the impossibly small, one that would challenge the very meaning of distance and connection. This story begins not with an experiment, but with a thought, a paradox so profound that its originator hoped it would prove a new theory of physics was fundamentally incomplete. Albert Einstein, the man who had himself appended classical physics with relativity, found the emerging ideas of quantum mechanics deeply unsettling. While he accepted its statistical accuracy, he believed it was an incomplete description of reality, a temporary theory that would eventually be replaced by something more deterministic, more sensible. In 1935, together with his colleagues Boris Podolsky and Nathan Rosen, Einstein formulated a brilliant mental critique designed to expose what he saw as quantum theory's fatal flaw. They envisioned a thought experiment now famous as the EPR paradox. Imagine a single particle decaying into two new particles. According to the conservation laws of physics, these two offspring must have properties that are perfectly correlated. For instance, if one has an up spin, the other must have a down spin to balance it out. Quantum mechanics said that until you actually measure one of them, both particles exist in a fuzzy, indefinite state of superposition, a blend of both possibilities. But here was the rub. The theory also said that the very act of measuring one particle, say, finding it to be up, would instantaneously force its twin, no matter how far away, to snap into the opposite state of down. This, to Einstein, was not just strange, it was impossible. It implied a mysterious, faster-than-light communication between the two particles, a violation of his own theory of relativity's cosmic speed limit. He derisively called this apparent connection spooky action at a distance. believing it was proof that quantum mechanics was not a full theory. He insisted there must be hidden variables, unknown properties predetermined at the moment of the particle's creation that we simply couldn't yet measure. For Einstein, the particles weren't communicating. They were just following a script written at their birth, like a pair of gloves separated at birth. If you find you have the left one, you know instantly the other is the right, without any spooky signal between them. For decades, this remained a fascinating philosophical debate, a war of ideas fought on chalkboards with no way to test who was right. The man who accidentally found a way to test it was a physicist named John Bell. Working primarily at CERN in the 1960s, Bell wasn't trying to prove entanglement real. He was a theorist trying to clarify the EPR argument, to see if Einstein's hidden variables could indeed be woven into quantum mechanics in a logical way. In a stunning piece of theoretical work, he derived a deceptively simple mathematical theorem, now known as Bell's theorem. This theorem provided a clear, testable criterion. If local hidden variables were real, if everything was predetermined and no spooky action was needed, then the results of certain correlated measurements on entangled particles would never exceed a specific statistical limit. However, if the bizarre predictions of quantum mechanics were correct and particles were truly connected across space, then experiments would violate this limit. Bell had, almost as a side effect of his deep thinking, created a recipe for an experiment that could finally settle the debate. The first experiments, conducted in the 1970s and 80s by physicists like Stuart Friedman, John Clauser, and Elaine Aspect, began to test Bell's inequalities. The setups were incredibly delicate, often involving pairs of entangled photons, particles of light whose polarization states were linked. The results were unambiguous and earth-shattering. Experiment after experiment showed a clear violation of Bell's limit. The correlations between the particles were stronger than any local hidden variable theory could possibly explain. The universe had chosen spookiness. When two particles become entangled, they truly do form a single, unified quantum system. Measuring one does indeed affect the state of its partner instantaneously, regardless of whether that partner is in the next room or on the other side of the galaxy. This non-locality is not a signal we can use to send information faster than light. The outcome of each measurement is still random, so no meaningful message can be passed. But the correlation is immediate and undeniable, a silent, instantaneous harmony that exists beneath the surface of reality. This accidental validation of quantum theory's weirdest prediction did more than just win a philosophical argument. It unveiled a layer of the universe that is deeply, fundamentally interconnected in a way that defies all our classical intuition about space and time. It suggests that at its most basic level, the universe is not a collection of separate, isolated objects, but a vast web of relationships where distance is an illusion for connected particles. This revelation is not just a theoretical curiosity. It is the foundational principle behind some of the most cutting-edge technologies of the 21st century. Quantum cryptography, for instance, uses the principles of entanglement to create communication channels that are fundamentally unhackable. Any attempt to eavesdrop on an entangled quantum key would immediately disturb the delicate connection, alerting the users to the intrusion. This is not just better security, it is security based on the unbreakable laws of physics. Even more transformative is the field of quantum computing. While classical computers use bits that are either 0 or 1, quantum computers use quantum bits or qubits, which can be 0, 1, or both at once thanks to superposition. But it is entanglement that provides their truly awesome power. By entangling many qubits together, a quantum computer can perform a vast number of calculations simultaneously. exploring many possible solutions to a problem in parallel. This could allow them to solve problems that are completely intractable for even the largest supercomputers today, from designing complex new medicines and materials by simulating molecular interactions directly to cracking the encryption codes that secure the modern internet. The seemingly abstract spookiness that so troubled Einstein is now being harnessed in laboratories around the world, pushing the boundaries of computation and opening doors to a future we are only beginning to imagine. The story of quantum entanglement is a powerful reminder that the universe's deepest truths often feel like magic, but they are governed by a precise and beautiful mathematics that, once understood, grants us not just knowledge but profound new power. Just as scientists were beginning to unravel the quantum spookiness governing the smallest particles, a far more tangible and immediate cosmic phenomenon was accidentally discovered right in our own planetary backyard, a discovery that would define the very challenges of leaving our home world. The year was 1958, and the space race was in its exhilarating infancy. The Soviet Union had just stunned the world with Sputnik, and the United States was desperate to catch up. Its answer was Explorer 1, a relatively small satellite hurriedly built and launched into orbit. On board was a scientific instrument package designed by a team led by the University of Iowa's James Van Allen. Its centerpiece was a Geiger counter, a device designed to measure the density of high-energy cosmic rays in space. The mission was a triumph, but the data it sent back was initially baffling. At certain altitudes, the Geiger counter's readings would spike to its maximum value and then suddenly drop to zero. At first, some scientists feared the instrument had simply failed. But Van Allen had a brilliant hunch. He suspected the counter wasn't broken, it was being overwhelmed. The radiation was so intense it was saturating the detector, causing it to shut down. It was like a light meter pointing directly at the sun. It couldn't handle the blinding intensity. Subsequent missions, including Explorer 3 and the Soviet Luna 1 probe, confirmed this spectacular suspicion. Explorer 1 had accidentally stumbled upon vast, donut-shaped zones of incredibly intense radiation encircling our planet, held in place by Earth's magnetic field. These were promptly named the Van Allen radiation belts in his honor. The discovery was a revelation. We learned that our planet is not simply floating in a passive, empty void. It is a dynamic, magnetic body actively interacting with the space around it. The sun constantly emits a stream of charged particles called the solar wind. When these particles approach Earth, our planet's magnetic field, or magnetosphere, acts like a protective shield, deflecting the majority of them. But some of these high-energy particles, primarily protons and electrons, become trapped by the magnetic field lines. They are funneled toward the magnetic poles, where they slam into the upper atmosphere and create the beautiful auroras. But a huge population of them gets caught in a perpetual electromagnetic trap, bouncing back and forth between the north and south magnetic poles in a high-speed dance, creating these zones of lethal radiation. This serendipitous find had immediate and profound implications. First, it revealed a natural planetary defense system. The Van Allen belts act as a buffer, absorbing and trapping a significant portion of the solar wind's most dangerous particles, protecting life on the surface from constant bombardment. But this protective cocoon also presented a formidable barrier to human ambition. These belts are not a safe place for living beings or delicate electronics. The levels of radiation within them are high enough to quickly cause radiation sickness in an unshielded astronaut and can fry the sensitive circuitry of satellites. This discovery single-handedly created the field of space weather research and forced a complete rethink of satellite and spacecraft design. Every single probe, communication satellite, and GPS unit destined for medium or high Earth orbit now had to be built with radiation-hardening special shielding to protect its vital components from this newly discovered environmental hazard. Most critically, it defined the challenge of human spaceflight beyond low Earth orbit. The Apollo missions to the Moon had to carefully plot their trajectory to pass through the thinnest possible regions of the belts, minimizing the astronauts' exposure time. They were essentially running a high-speed gauntlet through a zone of invisible fire. This unforeseen discovery, made with a simple Geiger counter on a rushed satellite, unveiled a fundamental aspect of our cosmic environment. It taught us that venturing into space isn't just about overcoming gravity. It's about understanding and surviving the complex and often hostile conditions that exist beyond our atmosphere. The Van Allen belts stand as a permanent reminder that our planet is an active participant in the solar system, and that every journey into the great beyond requires us to first understand the invisible forces that guard our doorstep. At the height of the Cold War, the United States launched a series of top-secret satellites with a singular, grave purpose: to watch for the telltale flash of gamma radiation that would signal a nuclear weapons test in the atmosphere or in space, a potential first strike by the Soviet Union. This project, known as Vera, was a crucial part of the nation's early warning system. The satellites were equipped with X-ray, gamma-ray, and neutron detectors, all meticulously calibrated to recognize the unique signature of an atomic blast. For the military personnel and scientists monitoring the data, every alert was a moment of supreme tension, a potential harbinger of global conflict. Then, in the late 1960s, the detectors began to ping with alerts that made no sense whatsoever. The signals weren't coming from Earth or its immediate vicinity. They were coming from deep space, and they didn't look like any nuclear test ever recorded. They were incredibly short, intense bursts of gamma rays that appeared randomly from all directions in the sky and then vanished without a trace. The initial reaction within the secretive corridors of the defense establishment was one of deep suspicion and high alarm. Had the Soviets developed a new, terrifying weapon of unimaginable power, one they were testing in the far reaches of the cosmos? Or was this some kind of elaborate jamming or spoofing technique? The data was classified, analyzed, and reanalyzed, but as more of these events were recorded over the years, a pattern emerged that pointed away from any terrestrial explanation. These bursts were isotropic, meaning they were coming from all over the sky with no preference for the plane of our solar system or the Milky Way galaxy. This was the crucial clue. If the sources were within our own galaxy, they would be concentrated along the band of the Milky Way. The fact that they were distributed evenly across the entire celestial sphere strongly suggested they were originating from far beyond our own galaxy, from the depths of the universe itself. The military, realizing they had stumbled upon a natural phenomenon of unknown origin, eventually declassified the data, handing astrophysicists one of the greatest mysteries of the 20th century. The scientific community was initially just as baffled. What natural process could possibly generate such an immense outpouring of the universe's highest energy form of light in such a fantastically short time? The early observations showed there were two distinct types of bursts: short bursts lasting less than 2 seconds, and long bursts that could go on for several minutes. Theories proliferated wildly. Perhaps they were caused by comets colliding with neutron stars, or by asteroids falling onto white dwarfs, or even by massive solar flares on stars within our own galaxy. For nearly 3 decades, the true nature of these gamma-ray bursts, or GRB, remained an enigma, their immense distance and fleeting nature making them nearly impossible to pinpoint and study. The breakthrough finally came in the late 1990s with the launch of the Italian-Dutch Beppo SAX satellite. which was uniquely equipped with both gamma-ray detectors and X-ray cameras. For the first time, when a long GRB went off, the satellite could quickly swivel to capture the fading afterglow of the event in X-rays and other wavelengths, providing a precise enough coordinate for massive ground-based telescopes to zoom in on. What they found was astonishing. The afterglow of these long bursts was linked to extremely distant, faint galaxies. The redshifts measured placed them billions of light-years away. This simple measurement solved the mystery and simultaneously unveiled a reality far more terrifying and magnificent than anyone had imagined. To be visible across such a mind-boggling distance, the energy release had to be almost beyond comprehension. In those few seconds of a gamma-ray burst, more energy is released than our Sun will emit in its entire 10 billion-year lifespan. For a fleeting moment, a GRB outshines the combined light of every star in its entire host galaxy. It is, by a colossal margin, the most powerful explosive event in the universe since the Big Bang itself. This realization immediately ruled out almost all the previous theories. Only the most catastrophic, ultra-violent cosmic events could possibly account for such staggering power. We now understand that there are two primary cosmic engines behind these awe-inspiring blasts. The long-duration gamma-ray bursts are now known to be the birth cries of black holes. They are associated with a specific type of supernova explosion, often called a hypernova, that occurs when the core of a truly massive, rapidly rotating star dozens of times the mass of our Sun collapses at the end of its life. This isn't just a standard supernova, it's a stellar death on an epic scale. The collapse doesn't just create a supernova remnant, it instantly forms a newborn black hole. As the star's outer layers come crashing down, some of the material is funneled by powerful magnetic fields into twin jets that scream outward from the star's poles at more than 99.99% of the speed of light. If one of those jets is pointed directly at Earth, we see the incredible flash of a gamma-ray burst. We are essentially looking straight down the barrel of the universe's most powerful cannon. The short-duration bursts have a different but equally dramatic origin. They are believed to be the result of the cataclysmic merger of two ultra-dense stellar corpses, either two neutron stars or a neutron star and a black hole. When these incredibly massive objects finally spiral together and collide after a billion-year dance, they create a violent tempest of ripples in space-time called gravitational waves, and for a fraction of a second, can also launch jets that produce a short, intense burst of gamma radiation. This accidental discovery, born from the paranoia of the Cold War, utterly transformed our understanding of the cosmos. It revealed a universe that is not the static, serene place it appears to be on a calm night, but a dynamic, violent, and often chaotic arena where stars die in spectacular fashion and new black holes are born in flashes of unimaginable power. GRBs are not just cosmic curiosities, they are crucial tools for astronomy. Because their light travels for billions of years to reach us, they act as probes of the early universe, allowing us to study the conditions and the rate of star formation when the cosmos was young. The 2017 detection of both gravitational waves and a short gamma-ray burst from the same neutron-star merger was a landmark event in multi-messenger astronomy, confirming the origin theory of short GRBs and opening a whole new window onto the universe. What began as a military project looking for the end of the world instead revealed a new class of cosmic catastrophe, proving once again that the pursuit of one kind of knowledge, even for defense, can accidentally illuminate the deepest workings of the universe. While the discovery of gamma-ray bursts revealed the universe's most violent explosions, a far more humble and delicious accident was taking place in a lab closer to home, one that would forever change the way we prepare our food. The year was 1945, and engineer Percy Spencer was deeply engrossed in his work for the Raytheon Corporation, which was producing magnetrons for radar systems critical to the Allied war effort. These magnetrons were the heart of radar, generating powerful microwave radio signals that could detect enemy ships and aircraft from miles away. Spencer was a brilliant, self-taught engineer with an intuitive understanding of electronics, and he was standing in front of an active radar set, testing a new magnetron design. It was a routine day of work until he reached into his pocket for a snack and discovered something utterly bizarre. The peanut chocolate bar he had stored there had been reduced to a gooey, melted mess. A less curious mind might have simply dismissed it as a coincidence, perhaps blaming body heat or the simple oddities of a cheap candy bar. But Spencer was a man known for his relentless inquisitiveness. Instead of wiping his hands and moving on, he saw a puzzle that demanded solving. He immediately began to experiment, systematically testing the effect of the magnetron's emissions on other foods. His next subject was a handful of popcorn kernels, which he held near the device. To his astonishment, they immediately began to pop, scattering all over the lab. Emboldened, he then tried an egg. A colleague famously stood by to watch, and the result was even more dramatic. The egg's internal pressure built up so rapidly from the intense heat that it exploded in the man's face. Spencer had conclusively proven that the microwaves emitted by the magnetron were responsible for this rapid and intense heating. He'd accidentally discovered a revolutionary new way to cook. The principle he stumbled upon is a beautiful example of applied physics. The magnetron generates electromagnetic waves with a very specific wavelength, microwaves. These waves are perfectly tuned to interact with water, fats, and sugars. Unlike conventional ovens that heat food from the outside in by transferring thermal energy through the air, microwave ovens work from the inside out. The microwaves penetrate the food and cause the water molecules within it to vibrate at an incredible rate, billions of times per second. This furious vibration creates molecular friction, which generates heat directly within the food itself. This is why a microwave can reheat a plate of leftovers in minutes, while a conventional oven would take much longer. It's directly energizing the molecules everywhere at once, not waiting for heat to slowly conduct inward. Spencer and Raytheon quickly recognized the potential of this accidental discovery. They filed for a patent and just 2 years later, in 1947, introduced the first commercial microwave oven. Dubbed the Radarange, it was a behemoth of a machine standing nearly 6 feet tall, weighing over 750 pounds and costing the equivalent of over $20,000 in today's money. It was cooled by water and consumed a staggering amount of electricity, making it a fixture only in large commercial kitchens like those of restaurants and railroad cars. It would take another 2 decades of refinement, miniaturization, and cost reduction before the microwave oven became an affordable and ubiquitous countertop appliance, truly revolutionizing domestic life around the world. The impact of this serendipitous moment extends far beyond the convenience of quick meals and defrosting frozen vegetables. Spencer's melted chocolate bar is a quintessential story of technological transfer, demonstrating how tools developed for war can be repurposed for profound peacetime benefit. The magnetron was designed to help win a world war by seeing the enemy at a distance. Its derivative technology now helps busy families prepare dinner. It underscores a recurring theme in innovation. The path from the laboratory to the living room is often unpredictable, guided by chance and the prepared mind of a curious individual. Furthermore, the microwave oven gave the general public a tangible, everyday connection to the invisible world of electromagnetic radiation. It made abstract concepts like wavelength and molecular excitation suddenly relevant, a practical demonstration of physics happening right on the kitchen counter. Percy Spencer's story is a powerful reminder that the line between a mundane observation and a world-changing invention is often drawn by a single person's willingness to ask a simple question: now, why did that happen? Meanwhile, in a London laboratory, a different kind of pattern was emerging, one that would unlock the very code of life itself. The quest to understand the structure of DNA was a fierce international race, with several brilliant minds convinced they were on the cusp of a monumental discovery. Among them was Rosalind Franklin, a gifted and meticulous chemist working at King's College. Her tool of choice was X-ray crystallography, a technique that involved shooting X-rays at a purified crystal of a substance and interpreting the intricate patterns they made as they scattered. It was painstaking, difficult work that required immense skill in both preparing perfect DNA samples and interpreting the complex, shadowy images they produced. Franklin was a master of the craft, known for her rigorous standards and sharp intellect. In May of 1952, after months of perfecting her technique, Franklin adjusted her equipment and focused the X-ray beam on a particularly fine fiber of DNA. The exposure took over 60 hours, capturing the subtle ways the X-rays were bent and diffracted by the molecule's invisible architecture. When she developed the resulting photograph, labeled simply Photo 51, she had in her hands one of the most important images in scientific history. To the untrained eye, it might have looked like a blurry cross of dots and smudges, but to an expert like Franklin, it was a treasure trove of information. The clear, crisp X pattern at the center of the image was the unmistakable signature of a helix. The angles and distances between the dark spots revealed precise measurements, the distance between the turns of the helix, its diameter, and the fact that the phosphate backbone of the molecule was on the outside. It was a stunningly clear, data-rich picture that pointed directly to a helical structure for DNA. The path this image took, however, would become one of the most debated episodes in the history of science. Franklin, a careful and cautious researcher, was systematically analyzing her data. She was focused on producing a complete set of evidence, planning to build a definitive model herself once all the pieces were in place. She was not yet ready to commit to a specific model, and she had, in fact, initially been skeptical of a helical structure. Without her knowledge or consent, her colleague Maurice Wilkins, with whom she had a strained and difficult professional relationship, showed Photo 51 to a visiting competitor, James Watson, who was working with Francis Crick at Cambridge University. For Watson and Crick, who had been pursuing their own theoretical model-building approach, seeing Photo 51 was a moment of breathtaking clarity. It was the key that unlocked the entire puzzle. The pattern confirmed the helical structure and provided the critical measurements they needed. It was the final piece of evidence that allowed them to correctly deduce the now iconic double helix structure, with its two strands running in opposite directions and paired bases on the inside like rungs on a twisted ladder. They immediately understood that this structure elegantly explained how genetic information could be stored and, crucially, replicated. The molecule could unzip, with each strand serving as a template for a new partner, ensuring the faithful transmission of the genetic code from one generation to the next. The publication of the Watson and Crick model in 1953, which included a passing acknowledgement that their work was stimulated by a knowledge of the general nature of the unpublished experimental results and ideas of Franklin and Wilkins, revolutionized biology. They had unveiled the secret of life's blueprint, a discovery that would earn them, along with Wilkins, the Nobel Prize in Physiology or Medicine in 1962. Tragically, Rosalind Franklin had passed away from ovarian cancer 4 years earlier at the age of just 37, making her ineligible for the award and cementing her place in history as the unsung hero of the story. This episode stands as a complex tapestry of brilliance, competition, and ethical ambiguity. It showcases how a single, exquisite piece of data, captured through skill and perseverance, can provide the crucial insight that leads to a paradigm shift. Yet, it also raises profound questions about collaboration, credit, and the ownership of scientific work. Would Watson and Crick have reached their conclusion without that unauthorized glimpse of Photo 51? Almost certainly, but it would have taken them much longer. Did Franklin's meticulous, evidence-first approach mean she would have inevitably put the pieces together herself? Many historians of science believe she was very close. The story of the double helix is a powerful reminder that the path to discovery is rarely a straight line. It is often messy, shaped by human relationships, chance encounters, and the sometimes uncomfortable interplay between competition and cooperation. It is a monument to the power of a single image to change the world, and a lasting testament to the critical, though often overlooked, role of a brilliant woman in one of science's greatest triumphs. Centuries before the invention of the telescope or the microscope, a mathematician in medieval Italy was pondering a far more down-to-earth problem: rabbit romance. Leonardo Fibonacci, in his 1202 book Liber Abaci, was trying to explain the advantages of the Hindu-Arabic numeral system to Europeans still clinging to Roman numerals. As a simple, illustrative exercise, he posed a theoretical problem about the ideal breeding conditions of rabbits. He calculated how many pairs of rabbits would exist after a year, assuming a pair produces a new pair every month, and each new pair becomes productive after 1 month. The solution generated a sequence of numbers 1, 1, 2, 3, 5, 8, 13, 21, and so on, where each new number is simply the sum of the two that came before it. It was a neat intellectual puzzle, a mathematical curiosity with no apparent application beyond his book. Fibonacci had no idea he had just sketched a hidden blueprint that the universe itself seems to follow. This seemingly abstract series, now famously known as the Fibonacci sequence, began its journey from mathematical oddity to cosmic principle when botanists and naturalists centuries later started noticing its patterns everywhere they looked. Take a close look at a pine cone and you'll see its scales spiral out from the center. Count these spirals and you'll almost always find the numbers 5 and 8, or 8 and 13 consecutive Fibonacci numbers. The same is true for the intricate arrangement of seeds in a sunflower's head. These seeds pack together with breathtaking efficiency, and to achieve this, they grow in spirals emanating from the center. Count the number of spirals curling to the left and the number curling to the right, and you'll get 2 consecutive Fibonacci numbers like 34 and 55. This isn't a coincidence, it's a masterclass in optimal packing. This specific Fibonacci-based arrangement, known as phyllotaxis, allows the plant to position each new seed at a specific angle related to the golden ratio, approximately 137.5 degrees, which ensures every seed has maximum access to sunlight and nutrients without being crowded out by its neighbors. It is the most efficient way to pack the most seeds into the smallest space, a strategy perfected by millions of years of evolution. But the reach of this medieval number sequence extends far beyond the garden and into the very heavens. When astronomers began to map the structure of our own Milky Way galaxy, they found it is a spiral with vast arms of stars and gas swirling out from a central core. These are not the static, rigid arms of a pinwheel. They are logarithmic spirals, a shape whose growth factor is intimately connected to the golden ratio derived from the Fibonacci sequence. This same spiral form appears in the terrifying beauty of a hurricane seen from space, in the delicate shell of a nautilus, and in the arrangement of planets in their orbits. The pattern recurs because it represents a fundamental principle of dynamics and growth in a rotating system. It is the shape of efficiency and balance, a form that allows for exponential expansion while maintaining a consistent, elegant proportion. The universe, it seems, has a preferred aesthetic, and it is written in the language of Fibonacci's numbers. This profound connection between a simple number sequence and the architecture of reality suggests something truly awe-inspiring, that the universe is not a chaotic accident, but is underpinned by a deep mathematical order. The laws of physics, the processes of biological growth, and the dynamics of cosmic formation all appear to converge on certain patterns that are not just efficient, but mathematically beautiful. The Fibonacci sequence is a bridge between the abstract world of pure mathematics and the tangible world of physical phenomena. It shows us that the logic of numbers is not a human invention, but a human discovery of a framework that is woven into the very fabric of existence. From the way rabbits multiply to the way galaxies spin, the universe consistently returns to this elegant, efficient pattern, proving that sometimes the most profound truths are hidden not in complexity, but in the simple, recursive beauty of a 700-year-old thought experiment. Christian Doppler's breakthrough began not with the silent, distant stars, but with the everyday sound of a passing train. As a mathematician and physicist in 19th-century Austria, he was deeply fascinated by waves, both sound and light. He theorized that the motion of a wave source should affect how an observer perceives those waves. To test his idea, he famously employed a group of trumpet players on a moving open railroad car. As the train sped past a station, musicians held a single, steady note. The listeners on the platform heard something remarkable. The pitch of the note was higher as the train approached and then distinctly lower as it receded into the distance. This wasn't a trick of the ear, it was a fundamental physical principle. The motion of the source was compressing the sound waves ahead of it, making them arrive more frequently and thus sound higher in pitch. As the source moved away, it stretched the waves out, making them arrive less frequently and sound lower. Doppler had accidentally quantified a phenomenon everyone had experienced, but no one had truly understood, giving the world the Doppler effect. His genius, however, didn't stop with sound. Doppler immediately realized that if this principle applied to sound waves, it should also apply to light waves, which were understood to be part of the same electromagnetic spectrum. He made a stunning prediction. A star moving toward Earth should have its light waves compressed, shifting them toward the blue end of the spectrum. Conversely, a star racing away from us should have its light waves stretched, shifting them toward the red end. This was a breathtaking leap. It suggested that by simply analyzing the color of starlight, we could determine not just a star's composition, but its velocity and direction through space. The universe, which had seemed static and silent, was suddenly singing a song of motion, and its verses were written in hues of blue and red. For years, this remained a brilliant but unproven theory. It wasn't until other astronomers, most notably Vesto Slipher and later Edwin Hubble, began to meticulously measure the spectra of distant galaxies that Doppler's prediction was spectacularly confirmed. They found that the vast majority of galaxies showed a pronounced redshift. Their characteristic fingerprints of hydrogen and other elements were all systematically shifted toward longer, redder wavelengths. This could mean only one thing: nearly every galaxy in the universe was flying away from us. This single observational fact, unlocked by Doppler's principle, became the cornerstone of modern cosmology. It was the primary evidence that led directly to the concept of the expanding universe and, by extension, the Big Bang theory. The faint reddening of ancient starlight was the universe's most important clue, revealing its dynamic, explosive origin and its ultimate fate. But the utility of this accidental discovery extends far beyond mapping the universe's expansion. The Doppler effect is one of astronomy's most versatile and powerful tools. It allows us to detect binary star systems where two stars orbit a common center of mass by watching their light rhythmically blue shift and redshift as they swing toward and away from us. It is the fundamental technique behind the discovery of exoplanets. We can't see these distant worlds directly, but we can detect the tiny, telltale wobble they impart on their host star. As a planet orbits, its gravity tugs the star ever so slightly, causing its light to very faintly red shift and blue shift in a regular pattern. By measuring this stellar dance, we can infer the planet's mass and orbital period. This same principle is used in police radar guns to catch speeding cars and in weather radar to track the motion of storms. From the grandest scale of cosmic evolution to the most mundane aspects of daily life, the Doppler effect proves that a simple observation, pursued with curiosity, can unveil a universal language of motion, allowing us to hear the rhythm of the cosmos in the shifting colors of its light. For over a century, black holes existed as the ultimate cosmic phantom, a mathematical certainty in the equations of general relativity, yet a thing most astronomers never expected to actually see. Einstein's theory described them as regions where gravity is so intense that nothing, not even light, can escape their grip. They are, by their very definition, invisible. How do you take a picture of something that consumes all light? The challenge seemed not just difficult, but fundamentally impossible. It would be like trying to photograph a shadow cast by an invisible object in a pitch-black room. Yet, this is precisely the audacious goal a team of scientists set for themselves with the Event Horizon Telescope project. They weren't trying to see the black hole itself, but its defining signature, the black hole's shadow, a dark silhouette against the glowing, superheated gas swirling around it. The plan was as brilliant as it was ambitious. To have any hope of resolving something so small and so distant, they would need a telescope with a resolution sharper than any instrument ever built. The target was the supermassive black hole at the heart of the galaxy Messier 87, a cosmic behemoth weighing in at 6.5 billion times the mass of our Sun. Despite its unimaginable size, its event horizon, the point of no return, would appear incredibly tiny in our sky due to its immense distance of 55 million light-years. To see it would require a telescope with a resolution equivalent to being able to read a newspaper in New York from a sidewalk cafe in Paris. Building a single dish that large is a physical impossibility. So the team did the next best thing. They turned the entire Earth into a virtual telescope. This is the magic of interferometry. By synchronizing a global network of radio telescopes, from the high deserts of Chile and the volcanic peaks of Hawaii to the frozen landscapes of the South Pole and the mountains of Spain, they could combine their data to simulate the resolving power of a planet-sized dish. The logistics were a nightmare of precision. Each observatory had to record its data using atomic clocks so accurate they would lose less than a second over the entire age of the universe. They needed perfectly clear, simultaneous weather at every single site around the globe. They gathered petabytes of data, so much information that it was actually faster to fly physical hard drives on airplanes to a central processing center than to try to send it over the internet. Then began the years-long, meticulous process of correlation and analysis, a digital symphony conducted by hundreds of scientists working in unison. The first observing run in 2017 was in many ways a high-stakes test of the entire concept. No one knew if it would work. The data was messy, filled with noise and uncertainty, but as they painstakingly assembled the fragments, a shape began to emerge from the chaos. It wasn't a clear picture at first, but a persistent pattern that matched their simulations. A bright, ring-like structure of intensely hot gas orbiting at near light speed, and at its center, a dark, circular void. This was the shadow of the black hole's event horizon, a region where gravity is so strong that it bends light paths into a circular trap, creating a perfect darkness outlined by a fiery ring. The image they released to the world in April 2019 was slightly blurry, but it was unmistakable. It was the orange, glowing donut that instantly became an icon, a visual proof of one of the most extreme predictions of modern physics. The significance of this accidental success during a test run cannot be overstated. That single image confirmed multiple pillars of general relativity in one fell swoop. The size and shape of the shadow matched Einstein's predictions perfectly. It provided direct visual evidence for the existence of an event horizon and the accretion disk of infalling material that theory had long described. But perhaps most importantly, it was a staggering testament to human ingenuity and collaboration. It showed that by uniting minds and technology across the entire planet, we could push the boundaries of observation to their absolute limit and make the invisible become visible. This wasn't just a picture, it was a portal allowing us to peer into the heart of darkness and finally lay eyes on one of the universe's most profound and elusive mysteries. Even as we began to map the grand architecture of the cosmos, a tiny, nagging inconsistency was emerging much closer to home. A whisper of something wrong in the seemingly well-understood space of our own solar system. The story begins with two intrepid robotic explorers, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these pioneers lived up to their name, becoming the first human-built objects to travel through the asteroid belt, the first to make close-up observations of Jupiter and Saturn, and the first set on a trajectory that would eventually carry them out of the solar system entirely. Long after their primary missions were complete, scientists at NASA, a jet propulsion laboratory, continued to track them using the Deep Space Network, meticulously measuring their position and velocity with breathtaking precision. They were marvels of navigation, their paths predicted by the immutable laws of orbital mechanics, a dance of gravity governed by the sun and the planets. But by the 1980s, as the twin spacecraft were billions of miles away, drifting into the frigid darkness beyond Pluto, the tracking data began to tell a strange and persistent story. Both pioneers were ever so slightly off course, not by much but consistently. An unknown force was acting upon them, producing a tiny, unexplained sunward acceleration, a deceleration of about 10 billion times weaker than the gravity we feel here on Earth. It was as if they were driving with a faint but constant pressure on the brakes. This minuscule discrepancy, which became known as the Pioneer Anomaly, was a classic case of a result that was too small to immediately dismiss as noise, yet too consistent to ignore. It was a tiny splinter in the finger of physics, a small data point that refused to fit the established model. For nearly 2 decades, this anomaly fueled a fascinating and intense scientific debate. Could this be the first hint of a deviation from Einstein's theory of general relativity? Perhaps gravity behaved slightly differently at the extreme edges of the solar system. Maybe it was evidence of something even more exotic, the gravitational pull of unseen, unknown matter, a local cloud of dark matter tugging on the spacecraft. Some theorists even proposed entirely new forces of nature or subtle modifications to the laws of inertia. the Pioneer Anomaly became a rallying point for those who believed our understanding of gravity was incomplete, a tantalizing clue that the next great revolution in physics might be hiding in the painstakingly precise Doppler shift of a radio signal from a dying probe. The eventual solution, painstakingly uncovered through years of forensic-level data archaeology and sophisticated new thermal modeling, was both more mundane and deeply impressive. The culprit wasn't a new force or hidden matter, it was heat. The pioneers were powered by radioactive thermoelectric generators, and they constantly emitted heat from their electrical systems and equipment. This heat radiation, while minuscule, was not perfectly symmetric. A slightly greater fraction of this thermal radiation was emitted from the warm, aft-facing sides of the spacecraft. According to the simple law of conservation of momentum, every photon of heat carrying energy away from the spacecraft also imparted a tiny, tiny amount of thrust in the opposite direction. This anisotropic heat rejection, this faint photon breeze, was pushing back on the probes, creating the precise sunward deceleration that had so baffled scientists. When this thermal recoil force was finally and meticulously calculated and factored in, the Pioneer Anomaly simply vanished. Yet, to dismiss this story as a simple case of a solved error is to miss its profound significance. The 2-decade-long investigation into the Pioneer Anomaly stands as a monumental testament to the scientific process itself. It showcases a fundamental truth: science often advances not when its predictions are confirmed, but when they fail. A result that doesn't fit the model is not a nuisance, it is an invitation to explore. The meticulous effort to explain this tiny drift pushed the boundaries of precision astronomy and spacecraft modeling to unprecedented levels. It forced scientists to account for every conceivable variable, from the subtle pressure of the solar wind to the faint glow of heat from a decades-old power source. In doing so, it ultimately strengthened our confidence in the very laws it seemed to challenge, proving that general relativity could withstand an incredibly precise test in a new regime. More importantly, the legacy of the Pioneer Anomaly is one of cultural vigilance. It taught an entire generation of physicists and engineers to never become complacent, to always treat an unexpected measurement with respect and curiosity. That ethos of anomaly hunting is now embedded in modern missions. When the New Horizons spacecraft flew past Pluto, its navigation team was acutely aware of the Pioneer story, meticulously modeling its own thermal emissions to avoid a similar puzzle. The search for tiny discrepancies continues to drive science, from the precise orbits of satellites around other planets to the mind-bendingly accurate measurements of distances with lunar laser ranging. The Pioneer's faint, unexpected signal reminds us that the universe is always speaking, sometimes in shouts like a gamma-ray burst, and sometimes in the faintest of whispers. The most important thing a scientist can do is listen carefully, especially to the things that don't quite make sense, for even a solved mystery can pave the way for the next great discovery. For centuries, the very existence of planets orbiting other stars was a matter of pure speculation, a dream confined to the pages of science fiction. Astronomers strongly suspected they were out there, of course. The process that formed our own solar system seemed too universal, too logical, not to be happening around other stars, but suspicion is not proof. The challenge was mind-bogglingly difficult. A planet, even a giant one, is astronomically small and incredibly dim next to the brilliant, overwhelming glare of its host star. Trying to see one directly would be like trying to spot a firefly hovering next from 1,000 miles away. The hunt required not a bigger telescope, but a smarter, more indirect method, one that looked for the planet's ghostly fingerprint on the star itself. That method was the radial velocity technique, often poetically called the wobble method. The principle is beautiful in its simplicity, rooted in the fundamental laws of gravity that Newton gave us centuries ago. We often think of a star holding its planets in orbit, a stationary anchor around which the worlds whirl. But this is only half the story. In reality, both the planet and the star orbit their common center of mass. For a star with a planet the size of Jupiter, this center of mass, or barycenter, lies just outside the star's surface. The gravitational tug of the planet causes the star to make a tiny, rhythmic dance around this point. From our distant vantage point, this dance appears as a subtle wobble, a slight shifting back and forth in space. The key to detecting this wobble lies in the same Doppler effect that revealed the expanding universe. As the star wobbles toward us in its tiny orbit, its light is very slightly blue-shifted. As it wobbles away, its light is red-shifted. By using a highly sensitive spectrometer to measure these exquisitely tiny shifts in the star's spectral lines over time, astronomers could not only detect the wobble, but also calculate the planet's mass and the length of its year. This was the theoretical backbone, but in practice, the measurements required were at the very bleeding edge of technology. The wobble induced by a giant planet might cause a star to move at a speed of only a few dozen meters per second, a walking pace. Detecting that from light years away is like measuring a change in a star's velocity with the precision of a gently drifting cloud. This is where our story finds its protagonists. In the early 1990s, Mitchell Mayer and his doctoral student Didier Queloz at the University of Geneva were not planet hunters. They were perfecting a new, incredibly precise spectrograph, a marvel of optical engineering they hoped would allow them to detect stellar wobbles with unprecedented accuracy. Their goal was to study binary star systems, to find small, dim stars like brown dwarfs orbiting larger companions. It was a rigorous test of their new instrument's capabilities, a calibration run on a list of nearby, sun-like stars. One of the stars on their list was 51 Pegasi, a star visible to the naked eye in the constellation Pegasus, about 50 light-years from Earth. As they collected their data night after night, a pattern began to emerge in the light from 51 Pegasi that was utterly bewildering. The star was wobbling all right, but the signal was shockingly strong and, even more bizarrely, it was incredibly fast. The data indicated a massive planet was tugging on the star, causing it to wobble with a period of just 4.2 days. This was the bombshell. A 4-day orbit meant this planet was orbiting breathtakingly close to its star, 20 times closer than Mercury is to our Sun. Based on the laws of orbital mechanics, they could calculate its mass about half that of Jupiter. They had found a Jupiter-sized world, but one that was searingly hot, orbiting its star in a blistering fast 4-day year. This was nothing like our own solar system, where giant, gaseous planets reign in the cold, spacious outer realms. According to every prevailing theory of planet formation, such a world simply could not exist. A gas giant couldn't form that close to a star. The intense heat and radiation would prevent the necessary gases from coalescing. Mayer and Queloz were initially skeptical, almost certain they had found some strange stellar phenomenon masquerading as a planet, or worse, an error in their own data. They spent months painstakingly checking and rechecking every possible variable, ruling out stellar pulsations, star spots, and instrumental glitches. But the signal was real, persistent, and unambiguous. With a mixture of trepidation and exhilaration, they announced their discovery in October 1995, an announcement that sent shockwaves through the astronomical community. The reaction was a blend of awe and intense skepticism. Here was a planet that broke all the rules, a world so strange it was nicknamed a hot Jupiter. Its existence forced a complete and immediate rewrite of the textbooks on planetary formation. Theorists scrambled to explain how a giant planet could end up so close to its star, proposing dramatic models of planetary migration where young, forming planets spiral inward through the protoplanetary disk, settling into these scorchingly close orbits. This single, serendipitous discovery, made while testing a new instrument, didn't just find one planet. It blew the doors off the field of exoplanet science. It was the spark that ignited a revolution. Almost overnight, other astronomers, armed with new confidence and refined techniques, began finding more of these strange worlds. The Kepler Space Telescope would later join the hunt, staring at a single patch of sky to find planets by the thousands using the transit method, watching for the telltale dimming of a star as a planet passed in front of it. We now know that planets are not the exception, they are the rule. It seems nearly every star has at least one planet, and many have complex systems of their own. We have discovered a staggering menagerie of worlds: super-Earths, mini-Neptunes, water worlds, and carbon planets. We have found planets orbiting binary stars like the fictional Tatooine, and planets drifting alone in the dark void between stars. The most profound impact of this discovery is how it has transformed our philosophical place in the universe. We are no longer wondering if other planets exist. We are now asking how many are Earth-like, orbiting in the habitable zone where liquid water could exist. The search for life beyond Earth is no longer a quixotic quest but a rigorous, data-driven scientific endeavor. The discovery of 51 Pegasi b by Mayer and Queloz, which earned them the Nobel Prize in Physics in 2019, fundamentally humbled us. It showed us that our solar system is just one possible configuration in a vast and wildly diverse galactic catalogue of worlds. It transformed our perspective from one of cosmic loneliness to one of potential cosmic community, revealing a universe that is not only vast and mysterious, but potentially filled with places where the incredible story of life might have found a way to begin again. Sometimes the most profound mysteries are hiding not in the distant cosmos or in a multi-billion-dollar laboratory, but in the simple, everyday act of making ice cream. This was the world of Erasto Mpemba, a secondary school student in Tanzania in the 1960s. During a cooking class, he and his classmates were tasked with making the frozen treat. In a rush to secure one of the limited spots in the school's freezer, Mpemba took a shortcut. Instead of waiting for his boiled milk and sugar mixture to cool down to room temperature like everyone else, he poured it into the ice tray while it was still hot and placed it directly into the freezer. To his complete astonishment, when he returned, his hot mixture had frozen solid before the cold mixtures of his classmates. He had just accidentally stumbled upon one of the most counterintuitive and hotly debated puzzles in all of physics. When Mpemba brought this observation to his physics teacher, he was met with dismissal and even ridicule. The teacher, and indeed the entire established body of thermodynamic knowledge, stated this was impossible. The logic seemed unassailable. For a hot liquid to freeze, it must first cool down to the temperature of the cold liquid. Since it has further to fall on the temperature scale, it should always take longer to reach the freezing point. Cold water has a head start. It should win the race to solidity every single time. Mpemba's result wasn't just unexpected, it seemed to violate basic common sense. But the young student, confident in what he had seen with his own eyes, refused to let the idea go. His persistence eventually led him to a visiting physics professor from the University of Dar es Salaam, Dr. Dennis Osborne. Intrigued by the boy's conviction, Osborne agreed to test the claim in a controlled setting. To his great surprise, the experiments confirmed it. Under specific conditions, the hot water did indeed freeze first. This phenomenon, which they would later document together in a published paper, became known forever as the Mpemba effect. The real mystery began not with the observation itself, but with the decades-long scientific quest to explain it. Why would hot water freeze faster? The answer, it turns out, is not a single magic bullet, but a complex cocktail of competing physical mechanisms that can conspire to give the hotter sample an unexpected advantage. One of the most significant factors is evaporation. The hotter water loses mass more rapidly to evaporation. Since there is less water left to freeze, the process can be completed more quickly. Think of it as a race where one runner suddenly has a shorter distance to cover. Furthermore, the act of evaporation itself is a cooling process, actively sucking latent heat out of the remaining liquid and accelerating its temperature drop. Another key player is convection. Hot water sets up powerful convection currents as it cools. The warmer water rises, the cooler water sinks, creating a constant churning that efficiently distributes the heat throughout the liquid and towards the surface where it can be lost to the surrounding freezer air. A container of cold water, by contrast, may develop a more stable temperature gradient with a colder top layer and a slightly warmer, insulated layer at the bottom. This stillness can actually act as a blanket, slowing the overall rate of cooling. There's also the role of dissolved gases. Hot water holds less dissolved air than cold water. As it heats up, these gases are driven out. Some scientists propose that this changes the water's properties, potentially affecting how heat is transferred or even how ice crystals initially form. Then there is the fascinating concept of supercooling. Cold water is more prone to supercooling, that is, it can dip below its freezing point 0 degrees Celsius while still remaining a liquid. This is a metastable state, and the water must then overcome an energy barrier to finally begin forming ice crystals. Hot water, which has undergone a more violent cooling process, may have fewer of the tiny impurities or nucleation sites that promote supercooling, allowing it to begin freezing right at 0 degrees and thus, in a way, catching up and even overtaking the cold water that is languishing in a supercooled liquid state. Some of the most modern research even delves into the bizarre world of quantum physics, suggesting that the hydrogen bonds between water molecules might have a memory of their previous warmer state, allowing them to snap into the crystalline structure of ice more readily. The story of the Mpemba effect is about so much more than just frozen water. It is a powerful lesson in the nature of scientific authority and the importance of intellectual humility. A student with a simple observation challenged a deeply held assumption that had gone unquestioned for centuries, simply because it seemed so logically obvious. It reminds us that science is not a collection of settled facts dictated from textbooks, but a living, breathing process of inquiry. It is a process that must always leave room for the anomaly, for the result that doesn't fit, especially when that result comes from an unexpected voice. Mpemba's curiosity and his courage to challenge an authority figure with evidence unlocked a puzzle that continues to inspire physicists and chemists to this day, driving research into non-equilibrium thermodynamics and the complex behavior of water, the most common yet most mysterious liquid on Earth. It stands as a beautiful testament to the idea that profound questions can arise from the simplest of places, and that a watchful eye in a school kitchen can sometimes see what an entire generation of scientists had overlooked. What emerges so vividly from these 25 stories is not a series of isolated flukes, but a powerful, repeating pattern in the very fabric of scientific progress. It's a pattern that reveals a profound truth about our relationship with the cosmos. The universe seems to prefer revealing its deepest secrets not to those who are merely diligent, but to those who are truly open. Time and again, we see that the critical ingredient wasn't a flawless hypothesis or a perfectly controlled experiment, but a mindset, a willingness to sit with an anomaly, to question an assumption, and to ask, what if? Instead of, that can't be, this is the golden thread connecting Pensier's and Wilson's pigeon droppings to Percy Spencer's melted chocolate bar. It's the shared trait of a researcher who, upon finding their experiment has failed, doesn't just sigh and start over, but leans in closer to ask why it failed in such a specific and interesting way. This pattern also shatters the myth of science as a purely linear, logical march toward truth. Instead, it shows us a far more human and dynamic process, one that is deeply iterative and wonderfully messy. Breakthroughs rarely happen in a straight line from question to answer. More often, they follow a jagged path of wrong turns, unexpected detours, and fortunate dead ends. The journey to understanding dark matter didn't begin with Vera Rubin setting out to find an invisible substance. It began with her simply trying to measure how galaxies spin, and having the courage to trust her data when it stubbornly refused to match the established theory. This process requires a form of intellectual humility that is perhaps a scientist's greatest asset, the ability to let the universe tell you what's true, even when it contradicts what you believe should be true. It's about being a perceptive listener in a grand, ongoing conversation with nature. Furthermore, these stories are a powerful testament to the collapsing boundaries between scientific disciplines. Some of the most revolutionary leaps occurred when a tool or a way of thinking from one field was accidentally applied to another. Alan Guth, a particle physicist, solved a monumental problem in cosmology with his theory of inflation. Wilhelm Röntgen's investigation into cathode rays, a topic in physics, accidentally gave medicine its most powerful diagnostic tool. This cross-pollination of ideas is where magic often happens. It suggests that the most fertile ground for future discovery may not be in the deep specialization of a single field, but in the vibrant, uncharted borderlands between them. The next great revelation might not come from an astronomer or a biologist, but from a bioastronomer or a discipline that doesn't even have a name yet. Underpinning all of this is the silent, enabling role of technology. Serendipity may provide the opportunity, but it is technology that gives us the means to seize it. Jocelyn Burnell could never have spotted the scruff of a pulsar without the massive radio telescope she helped build. The Higgs boson could never have been confirmed without the colossal, collaborative effort to construct the Large Hadron Collider. Our tools act as amplifiers for our senses, allowing us to perceive the whispers of the universe, the faint hiss of the Big Bang, the subtle wobble of a star tugged by an exoplanet, the fleeting flash of a gamma-ray burst. Each technological leap doesn't just provide better answers to our current questions, it inevitably reveals new and more puzzling phenomena we didn't even know to ask about, setting the stage for the next round of fortunate accidents. Ultimately, this recurring theme of accidental discovery carries a crucial lesson for how we foster innovation, not just in laboratories, but in our schools, our companies, and our cultures. It argues for creating environments that value curiosity-driven research, that allow for playful experimentation, and that don't punish so-called failure but rather see it as a vital source of data. It's about encouraging a state of mindful preparedness where we are constantly tinkering, observing, and questioning, so that when the universe offers up its next strange gift, we are ready to recognize it for what it is. The next fundamental law of reality is almost certainly not going to be found exactly where we are looking for it. It's hiding in the next piece of unexpected data, the next puzzling result, the next lucky mistake made by a curious mind who was paying attention. The greatest discovery we can make is to realize that the map to the unknown is drawn not with certainty, but with wonder. From the faint hiss of the Big Bang captured in a New Jersey antenna to the ghostly connection between entangled particles that so troubled Einstein, these 25 stories form a powerful testament to a single, beautiful truth. The universe does not yield its secrets only to those with the most meticulous plans or the largest budgets. Instead, it often whispers its deepest laws in the static of a failed experiment, in the glow of a forgotten screen, or in the stubborn persistence of a data point that simply will not conform. This is not a history of flawless genius, but a celebration of attentive curiosity, a chronicle of brilliant minds who, when faced with the unexpected, chose to lean in and listen rather than to dismiss and disregard. What these moments collectively teach us is that the greatest tool in science is not a telescope or a collider, though those are vital. It is a state of mind. It is the cultivated willingness to embrace the anomaly, to find the flaw in one's own understanding, and to have the courage to follow the evidence wherever it leads, even if it overturns everything we thought we knew. This journey has taken us from the heart of the atom to the edge of the observable universe, all sparked by accidents that became opportunities. They prove that the path to profound knowledge is rarely a straight line. It is a winding road built with equal parts preparation and luck, where a curious mind ready to capitalize on a chance encounter is the true catalyst for revolution. As we stand here today on the shoulders of these accidental giants, we have to wonder what mysteries remain hidden in plain sight. The next great law of physics, the solution to dark matter or dark energy, the true nature of consciousness, these answers likely won't be found exactly where we're looking for them. They are waiting in the next piece of unexpected data, the next puzzling result from a deep space probe, or the next curious observation made by a student in a classroom. The future of discovery depends on our continued commitment to fostering curiosity, to funding basic research whose applications we cannot yet foresee, and to teaching the next generation to not just learn the answers, but to cherish a good question. So, the next time you make a mistake or encounter a result that doesn't make sense, remember the stories of Penzias and Wilson, of Percy Spencer and Erasto Mpemba. Take a closer look, ask why. Your moment of surprise might not rewrite the laws of physics, but it could change your perspective in a profound way. The greatest takeaway from this journey is an invitation to everyone, not just scientists, to stay open to the wonders of the unexpected. Thank you for exploring these incredible twists of fate and fortune with me. If you enjoyed this dive into the serendipitous heart of science, be sure to subscribe and hit the bell for more adventures into the mysteries of the universe. I'd love to hear which accidental discovery amazed you the most. Share your thoughts in the comments below. And until next time, keep looking up and wondering.